Hello there, and welcome to Just About Earth, where curiosity settles in gently and the world's biggest questions are explored at a pace that lets your thoughts slow down instead of hurry. Tonight, we're drifting into one of the most unusual ideas ever proposed about our planet, one that sits quietly at the edge of science, not dismissed outright, not embraced entirely, but floating somewhere in that strange space where imagination and evidence occasionally nod politely to each other. It's called the Silurian Hypothesis, a simple but provocative question wrapped inside millions of years of geological layers and the deep, steady pulse of Earth's history. The question is this: if another industrial civilization existed long before humans, long before mammals ruled the land, long before our familiar continents and oceans settled into place, would we even be able to find it? The idea doesn't claim that such a civilization existed. Instead, it wonders whether the traces of one could survive long enough for us to notice. Because Earth is a patient recycler, a world that covers its past with new landscapes, new oceans, new forms of life, all while steadily erasing what came before. And if our planet is this thorough in cleansing its own history, then it's worth asking softly, without urgency or drama, whether we truly know everything about the past, or whether there are parts of it quietly missing, parts that no longer leave marks we can read. Before we wander too deep, I'd love to know where you're listening from tonight. Maybe you're curled up under blankets, maybe the lights are dim, maybe it's the end of a long day, and you're letting your mind drift into something comfortably strange. What time is it for you right now, in your corner of the world? Is it late enough that the sound of the evening is soft around you, or early enough that you're easing gently out of the day's busyness? It's always a curious thing to ask, especially when we're about to explore a topic that stretches across spans of time so large, our familiar clocks feel almost decorative in comparison. And if you find this slow exploration soothing, or thought-provoking, or simply a pleasant way to unwind, I'd be grateful if you gave this video a like or subscribed. It helps this quiet little corner of the internet float toward others who enjoy questions that don't need fast answers, only steady curiosity. The kind that doesn't demand conclusions but welcomes possibilities. So let's begin with a simple idea held lightly. Earth is very old. Older than civilization, older than humans, older than any stories we've ever told. It has passed through countless ages, each with its own climates, landscapes, and living things. When you think about deep time, not just thousands of years, but millions and hundreds of millions, it becomes clear that the world has reshaped itself again and again. Oceans have opened and closed, mountain ranges have risen and worn away, continents have collided and drifted apart, species have appeared, flourished, and vanished. And in all that changing and reshaping, the surface of the planet has rewritten itself many times over. Humans on this timescale are very new. Agriculture is only about 10,000 years old. The oldest recognizable civilizations stretch back perhaps 6,000 years. The entire span of recorded human history fits neatly into the last thin layer of geological time, a sliver so small it barely registers against the vastness beneath it. If all of Earth's history were a giant book, our part would be a final, thin page at the very end. The Silurian Hypothesis simply asks whether another page could once have existed far earlier in the book, long before humans arrived, and whether that page might have been erased. The name Silurian originally came from a group of ancient Earth layers dating back over 400 million years. Not because the hypothesis claims there was a civilization then, but because a fictional reptile species from an old television show was once given that name. The scientist who proposed the idea borrowed it with a hint of humour, not to suggest lizard people, but to acknowledge that the question itself, though serious, carries a certain whimsical curiosity. Not everything that sparks scientific thought has to come from solemn places. Sometimes a playful question is enough to open a deeper investigation. The real point behind the hypothesis isn't to prove lost civilizations, it's to understand the limits of the geological record. The Earth keeps many secrets simply because it is constantly renewing itself, Rock layers are buried, melted, crushed, eroded, and transformed. Ocean floors are swallowed back into the mantle. Coastlines rise and fall. If an industrial civilization much like ours had existed millions of years ago, would anything remain? Would the evidence survive the slow churn of plate tectonics, the pressures of deep burial, the cycles of erosion, or the chemical dissolving of the world's shifting environments? Or would the signs vanish completely, leaving us with a blank section of stone that quietly hides everything that once stood there? And this leads into deeper reflections about our understanding of Earth's past. We tend to picture pre-human history as vast stretches of forests, swamps, oceans, volcanoes, and drifting continents populated by animals and plants following long evolutionary paths. We rarely imagine machines or cities or artificial materials embedded in those ancient landscapes. But the hypothesis gently nudges us to consider whether our assumptions are shaped more by the absence of evidence than by the certainty of knowledge. After all, most of the signs of our own civilization, even the ones made from strong materials, will not survive for tens of millions of years. Our skyscrapers would crumble, our roads would fade, our metals would corrode, our plastics might last longer, but even they would eventually break down, buried or melted or altered beyond recognition. In the grand shifting of Earth, permanence is something we rarely achieve. Even today, when we look at geological layers, we often see only small traces of the environments that created them. A thin seam of clay, a layer of sandstone, a band of volcanic ash. These hold stories, but only partial ones, hints rather than full accounts. It's like trying to understand a lost culture from a handful of pottery shards. You can learn something, but you can't know everything. The deeper we dig, the more the past blurs, and at certain depths the picture becomes so faint that even entire global events can be hard to detect. If massive volcanic eruptions or meteor impacts sometimes leave only subtle traces in the rocks, imagine how easily the signs of a short-lived technological species might disappear. This isn't an argument that anything like that ever happened. It's a recognition that deep time is an eraser more powerful than fire or flood, or even human ingenuity. It smooths edges, dissolves details, and leaves behind only the most resilient remnants. And because the planet has been cycling its surface for billions of years, with entire oceans vanishing and reappearing, entire continents rising and falling, the question of what might be missing becomes more reasonable than strange. When scientists first presented this idea, they weren't suggesting we go looking for ancient cities under dinosaur fossils. They were asking a simpler, more grounded question. Suppose humanity vanished today. Imagine all our buildings, roads, tools, machines, satellites, and waste. Imagine the millions of artifacts we scatter across the land and sea. Now extend the timeline. 10,000 years pass, then 100,000, then 1,000,000, then 10 million. Ask yourself what would still be there, not through imagination alone, but through what we know about erosion, chemical weathering, tectonic movement, sedimentation, and the slow grinding pressure within the Earth's crust. Most of the obvious structures would be gone. The tallest buildings would collapse. The remains would break down into fragments. The fragments would crumble into grains. Vegetation would take over. Coastlines would shift. Rivers would carve new channels. Beaches would rise and fall. Deserts would form and vanish. Ice sheets would advance and retreat. And after a few million years, almost everything would be lost. That's the core of the Silurian Hypothesis. It isn't a tale of hidden civilizations or lost empires. It's an examination of how fragile the evidence of industrial society truly is when measured against geological time. When we think of a few thousand years as old, a few million can feel unimaginably vast. But the Earth deals in hundreds of millions and billions. Our place on that timeline is barely a breath. This gentle inquiry leads to all sorts of reflections, not about ancient beings or mysterious technologies, but about how we interpret the past at all. Geological records feel solid when we examine them. We see layers and fossils and mineral patterns and imagine them as complete narratives. but in truth, they are samples, fragments, a scattered collection of preserved moments chosen by chance rather than intention. Most moments are not preserved. Most layers vanish. Most organic matter disappears. Most traces are wiped clean long before anyone can discover them. It's also worth noting that Earth's oldest rocks have been recycled many times. Very little of the surface we walk on today is older than a few 100 million years. And the deeper rocks, the ones that might hold stories from earlier ages, are often transformed beyond recognition. Heat and pressure change them. Minerals rearrange, structures fold and break. If the rocks themselves can forget their origins, then it's not difficult to see how anything resting on them could fade as well. So as we start this journey, we hold the question gently. Not as something that demands belief, but as something that encourages us to think more carefully about how we read the past. It's not about discovering proof that someone else came before us. It's about understanding what the absence of proof can and cannot tell us. About learning how little of Earth's long story we actually see, and about recognizing that the world is full of unanswered questions, not because the answers don't exist, but because time has carried them away. When we try to imagine the world before us, our minds usually stop at familiar points. We might picture early humans walking across grasslands, or maybe huge mammals roaming icy plains, or even dinosaurs pushing through dense forests. But the Earth stretches back far beyond anything our imaginations reach easily. Trying to grasp that length of time is like trying to hold an ocean in cupped hands. No matter how tightly you try, most of it slips away. Still, even if the scale is overwhelming, there is a gentle calm that comes from sitting with it, letting the size of Earth's past settle around you without trying to shrink it into something small or straightforward. The planet has been here for 4.5 billion years, moving through ages so long and so varied that our entire existence occupies only the last narrow moment of its story. To get a sense of what came before us, you have to picture the Earth not as a background to human life, but as a world with its own long history. A world that changed its appearance, its atmosphere, its life forms, its temperature, its coastlines, and even its colours more times than we can count. The continents we know today weren't always here. The oceans we see on maps weren't always in their current places. Mountains that once towered into the sky have been worn down into grains. Vast oceans filled with ancient creatures have dried out and returned again. And through all of this shifting and reshaping, life appeared, diversified, endured, collapsed, and appeared again in new forms. People often imagine the distant past as simple or empty, but the truth is that ancient Earth was profoundly active. Volcanoes poured lava across landscapes we will never see. Seas full of unfamiliar organisms pulsed with their own rhythms. Entire ecosystems rose and fell across millions of years without leaving more than a few scattered traces. And everything we know about these worlds comes from evidence that survived only because it happened to fall in just the right place, at just the right moment. Most worlds that existed in the deep past left no sign at all. They were completely rewritten by time. That is one of the reasons the idea of the Silurian Hypothesis is so interesting. Not because it suggests hidden civilizations, but because it reminds us how short-lived the evidence of anything really is. When scientists look back into the deep past, they work with tiny fragments, layers of sediment, traces of isotopes, fossils that survived rare circumstances, minerals that managed to form under the right conditions. These fragments are scattered across the planet, much like a few pages from a book that once had thousands. Even with all the tools of modern science, we work from incomplete pieces, trying to recreate worlds that no longer exist. When you go back hundreds of millions of years, you're looking at a planet that doesn't resemble ours, not just in terms of animals and plants, but in how the entire surface was arranged. Continents drift, oceans expand or shrink, islands rise from the sea and disappear just as quickly. In some eras, Earth was warm enough that palm trees grew near the poles. In others, glaciers reached the equator. Each transformation erased the signs of what existed before it. Even something as basic as oxygen levels fluctuated dramatically across Earth's history. For long stretches of time, the atmosphere would have been unbreathable to modern humans. Before plants colonized land and began releasing oxygen on a large scale, the skies and oceans were shaped by completely different chemical balances. The creatures that lived during those times operated on biological rules that feel unusual to us, simply because our own lives rely on oxygen so heavily. But to them, it was normal. They were adapted perfectly to their environments, just as species today are adapted to ours. This is where an interesting realization starts to form. The Earth is not designed for humans. It never was. It simply happened that our particular biology fits the current state of the atmosphere, the temperatures we experience, the balance of gases, the distribution of land. But if you were to step outside that comfortable slice of time, even by a few 100 million years, you'd find a planet that would be strange and inhospitable to us. Yet for the species alive then, it was home. Perfectly normal. Perfectly suited. Think for a moment about the Cambrian period, more than 500 million years ago. The oceans were filled with animals that looked nothing like anything alive today. Some had bodies divided into multiple segments. Others had armor-like plates. Some had eyes on stalks. Others glided through the water using flaps or frills. It was a period of experimentation when evolution explored dozens of different pathways. And even though we have fossil evidence from that era, the fossils represent only a tiny fraction of what existed. Most species left no trace, not because they were unimportant, but because fossilization is a rare and selective process. Move forward to the Devonian or the Carboniferous or the Permian, and the Earth continues to show new faces. Entire forests rose and fell long before the first dinosaurs existed. In some regions, giant insects took to the skies because oxygen levels were high enough to support their enormous bodies. In others, amphibious creatures walked slowly across muddy land in a world that felt warm, humid, and dense. If you could stand in those ancient landscapes for a moment, even quietly, you would see a world that feels familiar in some ways, but completely alien in others. Rivers still flowed, rain still fell, mountains still rose, but the life forms filling the spaces were different, shaped by rules that don't apply anymore. Then there were mass extinctions, times when the Earth changed so quickly and so dramatically that most species vanished. These events reset the planet repeatedly, clearing ecosystems and allowing new ones to take their place. Each extinction erased enormous amounts of biological history. Entire lineages disappeared. Fossil records show breaks, gaps, sudden shifts from one type of world to another. After each collapse, the Earth rebuilt itself, but never in the same way. That constant rebuilding is part of what makes the deep past so hard to interpret. The evidence left behind is only what managed to survive all the reshaping. Think about human structures for a moment. Our buildings, roads, vehicles and tools feel solid. But compared to Earth processes, they're temporary. If you walk through an abandoned town after only a few decades, you already see nature reclaiming it. Plants break through pavement. Metal rusts. Roofs collapse. In only a few hundred years, most structures become indistinguishable piles of debris. Extend that to a few thousand, and those piles blend into soil layers. Extend it to a few million, and nothing recognizable remains. Now imagine trying to find traces of anything that existed 200 million years ago. Even fossils from that time are rare. Even mountain ranges from that time are worn down. The ocean floors from that time have been consumed by tectonic plates. The world that existed then is gone. Not because it wasn't real, but because Earth is always in motion. When scientists study these eras, they don't look for individual objects. They look for patterns, shifts in carbon levels, changes in sediments, traces of volcanic activity, chemical signatures left by ancient oceans, fossil transitions from one species to another. These subtle clues allow them to piece together what the world was like, not through complete narratives, but through careful interpretation. Looking at the Earth before us means accepting that we are working with fragments. It means understanding that what survives is not a full account, but a selective collection of remnants that manage to avoid destruction. And this makes the question raised by the Silurian Hypothesis more understandable, not as a claim that something existed, but as a reminder that absence is not always the same as certainty. When most things vanish from the record, even dramatic events can be reduced to faint traces. And if that's true for natural processes, it would also be true for anything else that might have occurred. The Earth, before humanity, passed through stretches of calm and stretches of chaos. Catastrophic extinctions were followed by flourishing recoveries. Entire ecosystems rose in richness and complexity, then disappeared completely. Continental collisions created mountain ranges that later eroded into plains. Oceans swallowed coastlines and later receded to expose new land. The atmosphere thickened, thinned, warmed, cooled, and shifted in composition. This constant motion, this constant reshaping, is what makes Earth both fascinating and challenging to read. Even the continents themselves carry memories only in certain places. Much of the crust has been recycled. The ocean floors renew every 200 million years or so. That means anything that happened before that time on the ocean floor is gone entirely. On land, older rocks exist, but they have been folded, heated, and crushed. They hold chemical hints of what once lay above them, but not detailed records. If you want to find evidence of ancient life or ancient environments, the places where preservation is possible are fewer than most people realize. Sitting with this perspective helps us understand how young humanity is. Our civilizations occupy only the final sliver of the timeline. Everything familiar to us, from writing to agriculture to technology, fits into the last tiny moments of Earth's story. Not because we are unimportant, but because the scale is enormous. Thinking about this doesn't diminish humanity. Instead, it gives us a wider perspective, one that opens up questions rather than closing them. One of those questions is simply this: if Earth has hosted so many worlds before us, each different from the last, how complete is our understanding of those worlds? How much do we see, and how much has slipped away? And if the evidence of natural events fades so easily, what could we realistically expect to find from anything that didn't last long, or didn't leave robust geological marks? These aren't questions meant to unsettle. They're questions meant to remind us that the Earth is vast, active, and constantly renewing itself. It is not a museum of the past. It is a living, changing planet. When we look back, we're not just seeing ancient landscapes, we're seeing the limits of how those landscapes can be reconstructed. And acknowledging those limits is part of understanding the planet's long history. It doesn't suggest hidden civilizations. It doesn't imply secret histories. It simply points out that deep time is thorough in its ability to reshape everything. When people hear the phrase ghost civilizations, their minds often jump straight to legends, hidden cities, or imaginative stories about lost cultures quietly erased by time. But the idea we're exploring here doesn't point toward fiction or myth. It starts from something much simpler. When scientists look back into Earth's deepest past, they notice something that feels almost like pages missing from a book. Entire stretches of geological time contain fewer clues than we would expect, not because anything mysterious happened, but because the ways in which Earth preserves its own history are selective. In some eras, the rocks are generous with information, and in other eras, they fall silent. This silence is what invites the question. If the planet can erase so much naturally, if entire worlds disappear simply due to the slow shifting of continents, erosion, heat, and pressure, then how much confidence can we place in what isn't there? When we look for evidence of early life or early climate or early environments, we find only what happened to survive. The rest is gone. And once you accept that nature forgets most of what it creates, The idea of an empty page becomes less dramatic and more of a natural consequence of deep time. To understand the idea of ghost civilizations in the context of the Silurian hypothesis, we have to avoid imagining anything elaborate or impossible. This isn't about cities made of stone still standing beneath jungles. It's not about pyramids buried under oceans. It's not even about lost cultures the way we think of human societies from a few thousand years ago. The term civilization, in this context, is used very differently. It refers to any species that might have achieved an industrial level of development long before humans existed. Not millions of years ago, but tens or hundreds of millions. Long enough that every trace we would normally expect from human activity today would have been erased. But before we go there, it's important to sit with what makes the idea even worth examining. It begins with the simple fact that the geological record is incomplete. Scientists know this not because they suspect hidden civilizations, but because they study rocks and see what's missing. There are gaps where entire sediment layers should exist but have worn away. There are regions of the world where the rocks that ought to record specific time periods simply don't exist anymore. They were eroded, subducted, melted, or otherwise removed. In some cases, the gaps represent a few thousand years, in others, tens of millions. These gaps are called unconformities, and they are common. They appear on cliffs, in road cuts, on canyon walls, and in the cores drilled for scientific research. When you see one, you're looking at a literal missing page. The rock record jumps from one time period to another, sometimes skipping enormous spans that once contained landscapes, oceans, life forms, ecosystems, climate cycles, and entire worlds that left no surviving trace. The Earth doesn't preserve its past with the intention of helping us. It preserves only what it happens to keep. Because of this, scientists regularly encounter places where very little evidence remains from specific stretches of time. An entire 20 million year window might be captured only by a thin layer of rock. Another 100 million year period might appear as only a few scattered formations across the entire planet. And when those formations exist, they often represent limited environments. Maybe a shallow sea, maybe a volcanic plain, maybe a lake bed. They rarely show a full picture. They show one environment, fossilizing one type of organism under one set of conditions. Everything else from that era is simply gone. When you take this into account, you start to understand how difficult it would be to find evidence of anything rare, short-lived, or confined to a small geographical region. This applies to species, ecosystems, climate events, chemical changes, and certainly anything produced by a hypothetical technological species. If we have trouble finding fossils of species that dominated the world for millions of years, imagine trying to find traces of something that might have lasted only a few 100,000. Even many major mammal lineages from recent geological time are represented by very patchy fossil records. Entire types of animals appear suddenly in the rocks, not because they truly appeared overnight, but because the softer, earlier evidence didn't survive. Earth is constantly recycling itself. The oceans open and close, mountain ranges rise and then wear away. Sediment accumulates in one place while disappearing from another. Tectonic plates carry entire continents across the globe. Volcanoes erupt and bury landscapes, only for those layers to erode millions of years later. The processes never stop. Every part of the crust is in motion. Even the oldest rocks on the planet are not untouched remnants of the earliest ages. They have been heated, folded, compressed, and altered. Whatever they once recorded is blurred, transformed, or erased. This reality leads to a calm but significant realization. The past is not stored the way we might imagine. There is no complete archive. There is no giant library of stone where every era is neatly documented. Instead, the planet keeps only fragments, some preserved by chance, some by unusual environmental conditions, some by chemical stability, most lost. When we think about ancient civilizations in the human sense, we imagine physical structures, walls, temples, roads, metal tools, pottery, artwork, houses, monuments. These things last for centuries or millennia if left alone. We find them in deserts, forests and riverbanks. We excavate them from beneath modern cities, but scale those objects against millions of years and they become temporary. A concrete building might crumble within a few hundred years. A steel bridge might rust away in a few thousand. Modern plastics might persist longer, but they too break down eventually into smaller fragments that disperse. If buried deeply enough, heated enough, or compressed enough, they would vanish entirely. This isn't speculation. It's something we can observe even in the relatively short spans of human abandonment. Towns overtaken by vegetation within decades. Factories collapsing into piles of rubble. Structures consumed by erosion, moisture and time. When you extend the timeline, the disappearance becomes inevitable. Given enough time, even robust materials dissolve, oxidize or transform. If a city were left untouched for 1 million years, nothing recognizable would remain. Extend that to 10 million or 100 million, and the record becomes not just faint, but non-existent. This brings us back to the empty pages in stone. If something leaves no trace, the absence doesn't necessarily prove it never existed. It simply means the evidence didn't survive. This principle is central to how scientists interpret the deep past. But it also raises a gentle question that sits at the heart of the Silurian hypothesis. If most of Earth's history is missing, and if even enormous natural events sometimes leave only subtle marks, then how confident can we be that we would detect something exceptionally rare or brief? The authors of the hypothesis weren't suggesting that such civilizations existed. They were asking whether the rock record is complete enough to rule the idea out entirely. It's a question rooted in geology, not mythology. It's a way of examining how we understand the planet's long story and the limits of the evidence we rely on. Take the example of the Paleocene-Eocene thermal maximum, a major climate event about 56 million years ago. This event involved significant global warming, massive carbon releases, shifts in ecosystems, and widespread changes in the oceans. It lasted for thousands of years and affected the entire planet. Yet the evidence for it is surprisingly subtle. It appears as small chemical signals in scattered sediment samples. A bit more carbon here, a slight shift in oxygen isotopes there. Enough to show something happened, but not enough to directly reveal the source of the carbon. Scientists have theories, but the event still holds uncertainty. If such an intense global shift leaves only faint clues, what would happen to something smaller or more localized? The deeper you look into time, the clearer the answer becomes. It would vanish, and once it's gone, the rocks don't leave behind a blank label saying something was once here. They simply record what happens next. Another example is the Permian-Triassic extinction event. It was the largest mass extinction in Earth's history, wiping out the majority of species. Yet the evidence is limited by where rocks from that era happen to have survived. In some places, the transition between eras is clear. In others, it's incomplete. In many parts of the world, it's missing entirely. A global catastrophe, the greatest known, is barely preserved. That context makes the idea of missing chapters far less surprising. So when people hear the term ghost civilization, it's easy to think of something fantastical. But what's meant here is much quieter. It refers to the possibility that, even if something remarkable had occurred in some distant age, the traces could have been erased completely through natural processes. The ghost is not the civilization. It is the gap in the record where something might have existed but left nothing behind for us to examine. And that brings us to why the idea feels intriguing. It doesn't rely on speculation about who might have lived or what they might have built. It doesn't rely on storytelling. It relies on the simple observation that Earth forgets almost everything. Knowing this doesn't suggest anything unusual happened. It simply creates space for a thoughtful question about what the geological record can and cannot reveal. And thinking about it helps us reflect on how fragile our own place is. How much of what we create, despite feeling permanent to us, is temporary in the grand scale. How easily our part of the story could vanish and leave no signs for whatever comes after us. As we keep moving forward into this exploration, the idea of missing pages becomes more than a curiosity. It becomes a way of understanding how we read the planet, how we interpret the faint signals it preserves, and how much remains unknown simply because Earth is always changing. When you look at a timeline of Earth's history printed on a page, it seems neat, almost organised. The dates progress in a straight line, the eras line up one after another, and each event fits into a tidy label. But if you try to imagine the real thing, the actual process of reading time from rocks buried deep in the ground, the simplicity disappears. Geological time is not laid out like a timeline or a calendar. It's layered, broken, shifted, scattered, folded, erased, rewritten, and in many places simply missing. Understanding it is less like reading and more like assembling a puzzle when most of the pieces are gone. A few pieces belong to other puzzles entirely, and the ones you do have are cracked or stained by millions of years of pressure. This puzzle is what geologists work with every day, and when scientists discuss the Silurian Hypothesis, they aren't leaning on speculation. They are acknowledging that the puzzle itself has gaps so large that we sometimes forget how incomplete the picture truly is. The rocks record something, but rarely everything. They capture moments instead of whole stories. They give us impressions, hints, fragments, and from those fragments we build our understanding of ancient Earth. To get a sense of why this matters, consider how the rock cycle works. Every piece of crust on Earth, whether exposed on a mountainside, buried beneath a valley, or hidden deep under the ocean, is part of a constant, slow transformation. Sedimentary rocks form from layers of particles deposited by water, wind, or ice. Igneous rocks form from cooled magma. Metamorphic rocks form when heat and pressure reshape existing rocks into something new. Each type can turn into another under the right conditions. It's a slow but relentless process, and over millions of years it destroys far more information than it preserves. Imagine a sedimentary layer forming at the bottom of a quiet ancient sea. It collects fine particles, maybe shells, maybe microscopic organisms. Over thousands of years it thickens, over millions it becomes rock. But then the sea drains away. The land rises, new layers form on top. Then tectonic plates shift. The once flat layers tilt sideways. Pressure increases. The rocks fold, crack or break. Some layers are uplifted above ground and erode. Others are buried deeper. If the pressure becomes intense enough, those sedimentary rocks metamorphose, losing fossils and structures as they transform. If they sink far enough, they melt and become magma, ready to emerge later as new igneous rock somewhere else. In the end, that calm seabed from millions of years ago becomes something entirely different. It may leave no visible sign of what it once recorded, and this is only one small part of the puzzle. The Earth repeats these processes everywhere, all the time. Layers form, layers vanish, and new layers take their place. So when scientists find a piece of rock that preserves a particular moment from the past, it's not because the planet tried to save it. It's because that piece happened not to be crushed, melted, or scraped away. It is a survivor of chance. Now imagine trying to interpret the whole history of Earth from these survivors. That is the challenge of geological time. We read whatever pieces remain and try to fill the gaps without assuming too much. Some eras are rich with data, others have almost nothing. The richness or emptiness rarely reflects what actually happened at the time. It reflects what managed to stay intact. This is why the puzzle analogy works. You rarely know how many pieces are missing. You rarely know what the full picture looked like. And sometimes you don't even know whether the pieces you have represent the most important events or only random moments that happen to fossilize well. Take the Precambrian, which accounts for roughly 88% of Earth's history. Nearly all of it is poorly preserved. Only certain rocks remain. most of which have undergone multiple phases of heating and deformation. It's like trying to reconstruct someone's life story from a few faded photographs taken decades apart. In some cases, vast stretches of time appear in rocks only through chemical traces locked in minerals. The events themselves have been erased. Even more recent eras show similar problems. The early Cretaceous period, which supported an enormous diversity of dinosaurs, is recorded unevenly across the globe. Some regions have detailed fossils from the time, others have none. Whole continents lack rock layers from certain spans of millions of years. Those gaps are not intentional. They simply reflect where sediments were deposited, where erosion was heavy, and where tectonic activity erased the record. This unevenness leads to a quiet but important realization. When we say, we have no evidence something existed, we usually mean nothing survived for us to find. But that is not the same thing as saying nothing existed. It is simply an acknowledgement of the puzzle's empty spaces. Understanding the puzzle buried in geological time involves looking not only at what the rocks show, but at what they cannot show. For example, consider ocean floors. The entire crust beneath the world's oceans is replaced roughly every 200 million years. It forms at mid-ocean ridges, spreads outward, and is eventually dragged back into the mantle at subduction zones. That means any record older than 200 million years that existed on an ancient ocean floor is gone. Not eroded, not buried, gone completely, melted and recycled into new rock. If something significant happened on the seafloor 300 million years ago, there would be no direct evidence left. If something happened 1 billion years ago, the situation is the same. Most of Earth's surface has been renewed multiple times. Only certain continental regions contain rocks older than 200 million years, and even those rocks have changed. Picture how this affects our ability to reconstruct ancient history. Imagine a hypothetical species that lived near coastlines, or on islands, or in low-lying areas, as humans do today. Most of those environments sit on oceanic crust or in places prone to flooding or erosion. If that species disappeared millions of years ago, the evidence of its activity would almost certainly vanish. Only a very small number of geological conditions could preserve traces long enough for scientists to find them today. Even on land, erosion strips away evidence relentlessly. Think about a mountain range. At first it rises dramatically. Over time, rain, wind, ice and gravity wear it down. Sediments wash into rivers and travel to basins. Eventually the mountains shrink. After tens of millions of years, the landscape changes so completely that nothing remains of the original peaks. The same is true for valleys, floodplains, coastlines and lakes. They form, shift and disappear. If a species built structures in these environments, the odds of preservation over geological timescales approach zero. Fossils illustrate this point clearly. Fossilization requires specific conditions. A creature must die in a place where it will be buried quickly, protected from scavengers and decay. It needs the right chemical environment. Even then, the fossil is fragile. It can be destroyed by erosion, heat, or pressure. Only a tiny fraction of all life that ever existed became fossilized, and only a tiny fraction of those fossils have been discovered. This selective preservation means the fossil record is like a photograph album with most of the pages missing. We see snapshots, not the full story. If entire species, ecosystems or events left no fossils, we cannot assume they didn't exist. We can only say we haven't found evidence. This leads to one of the most important aspects of the puzzle. The older the time period, the fewer pieces remain. Geological time is like a long corridor with many doors. Some doors open easily and show clear scenes. Others are jammed or missing. Some open onto empty rooms where the walls have been stripped bare, and some are sealed entirely, with no way to see what was once behind them. Scientists rely on chemical signatures, isotope ratios, mineral patterns and sediment analysis to piece together what they can. But even these tools have limits. For example, A major climate shift might leave a recognizable chemical signal, but the cause of the shift might not. A large volcanic eruption might leave ash layers, but erosion might remove them later. A massive impact might leave microscopic traces, or those traces might dissolve over time, and an industrial civilization, if it were small or short-lived, might leave signals too faint to distinguish from natural variations. That is not an argument that such civilizations existed. It is simply a recognition that the geological record is not all-seeing. It captures some moments with clarity and misses others entirely. And because the Earth continuously changes, we should not assume that we are looking at a complete record. Another important piece of the puzzle is how rocks are exposed. Even if a layer survives underground, it remains hidden unless erosion or uplift brings it to the surface. Much of Earth's crust is locked beneath soil, vegetation, water, or younger rock. Scientists can only study the layers they can reach, and those layers represent only a fraction of the total record. Consider that more than 70% of Earth is covered by oceans today. Much of the remaining land is covered by forests, grasslands, deserts, glaciers, or cities. The areas geologists can access are limited. Even when they drill into the ground, they sample only narrow sections. They can't extract continuous cores from every region. As a result, the puzzle will always be incomplete. This incompleteness is part of why the Silurian hypothesis is scientifically valuable, even if its conclusions are not dramatic. It encourages experts to think carefully about what the record does and does not show. It pushes them to consider the possibility of blind spots. It highlights how easy it is to mistake absence for certainty. And it reminds us that deep time is too vast for humans to imagine clearly. When you picture the last 100 million years, the scale feels enormous. But in geological terms, that span is only one part of Earth's long story. Dinosaurs dominated the land for more than 160 million years. Trilobites lasted for nearly 300 million. If an industrial civilization had existed for even 1 million years, a much longer time than humanity's current industrial period, it would still be a brief moment compared to those long eras. And even those long eras left uneven and incomplete fossil records. Now imagine trying to find evidence of a brief industrial period in rocks hundreds of millions of years old. The fragments we rely on today might not survive long enough. The chemical traces might be indistinguishable from natural cycles. The sediment layers might not form in the right conditions, and tectonic activity might recycle the crucial layers before they can be preserved. Thinking about the puzzle in this way doesn't imply that hidden civilizations are waiting to be discovered. It simply emphasizes how intricate and selective Earth's preservation processes are. And understanding those processes gives us a more grounded sense of why empty pages appear in the geological record and why we must read each piece cautiously. It's surprising how little of our world would endure if time were allowed to move forward without interruption. Not surprising in the sense of being shocking or dramatic, but surprising in a quiet, practical way. We tend to think of human structures as solid. Bridges feel heavy. Skyscrapers seem permanent. Highways stretch so far across landscapes that they give the impression of stability. Yet when you place these things against a backdrop of 1 million years, their resilience becomes far less certain. Time, especially deep geological time, doesn't just wear things down, it replaces them. To understand what evidence truly survives, the first step is letting go of the idea that durability is measured by human standards. The things we build are impressive to us because they last longer than our lifespans. A building that remains standing for 2 centuries feels ancient. A monument that endures for 1,000 years feels almost eternal. But to the Earth, 1,000 years is a blink. 1 million years is a slow breath. Anything designed on human timescales is temporary by default. Take concrete, for instance. It's often thought of as one of the strongest materials we use. Roads, dams, tunnels and skyscrapers rely on it. Yet concrete breaks down under weathering, water movement, chemical changes and biological growth. The reinforcing steel inside it rusts, cracks spread, pieces fall. Within tens of thousands of years, exposed concrete turns into crumbs. Within 100,000, even the buried sections degrade, particularly if groundwaters shift or temperatures fluctuate. In 1,000,000 years, the original shape and purpose would be almost impossible to detect. It wouldn't resemble a structure. It would resemble a patch of rock fragments. Metal corrodes even faster. Steel, iron, and aluminum react naturally with oxygen and water. Even stainless steel slowly loses its integrity. A few thousand years is enough for most metal artifacts to become unrecognizable. A few 100,000 years will erase them entirely. Over 1,000,000 years, all the metal objects from a modern city would return to the environment as dissolved elements or mineral grains inside sediments. Their shapes, edges, and purposes would be gone. Now think about plastics. They often come up in discussions about future geological layers because many of them degrade slowly. But slowly is a relative term. Plastics break down under UV light, heat, mechanical stress, and chemical reactions. They fragment. They become brittle. They turn into microplastics. These pieces continue to break down into smaller particles. Eventually, even those particles degrade further or become incorporated into sediments. If buried deep enough, they may transform chemically. 1,000,000 years could reduce them to carbon compounds that blend seamlessly with natural materials. Their artificial origin would be difficult to detect without extremely detailed analysis, and in many cases the record would disappear entirely. Buildings made of glass fare no better. Glass is not a perfectly stable solid. It can devitrify, meaning it transforms into more stable crystal structures over long periods. It can dissolve slowly in certain groundwater conditions. Under pressure, it can deform. And once a building collapses and the glass is exposed to physical stress, the fragments merge with the surrounding environment. After 1,000,000 years, even large quantities of glass might not leave recognizable traces. Even our most iconic structures, skyscrapers, dams, bridges, tunnels, monuments, would not remain in any form we would identify. Erosion would wear them away layer by layer. Vegetation would break them apart. Animals would burrow through them. Earthquakes would reduce them to piles of rubble. Floods and landslides would cover them. Water flow would transport the debris. And eventually sediments would bury everything, placing the remains into a geological context where pressure, temperature, and chemical reactions alter them beyond recognition. If all of this is true for the strongest and largest objects we create, it naturally extends to smaller items. Books, fabrics, electronics, furniture, pavements, vehicles, and tools. All of them vanish much faster. Their materials disintegrate quickly. Their shapes do not survive. Their functions cannot be guessed from the fragments that remain. On human timescales, objects feel lasting. On geological timescales, they disappear soon after they form. This raises the question that scientists ask when discussing the Silurian Hypothesis. If our current civilization ended suddenly and the planet continued on as normal for 1,000,000 years, what evidence would remain? What would a future species, if one ever evolved, be able to find? Not the objects themselves, but the deeper signals. One of those signals is chemical. Our industrial society releases unusual compounds into the environment. These include plastics, synthetic chemicals, industrial byproducts, and certain isotopes. Some of these compounds could, in theory, become trapped in sediment layers, but the reliability of that trapping depends heavily on where they land. Sediment accumulates at different rates depending on the environment. In some places, a thick layer might form over a short period. In others, no sediment accumulates at all. If materials settle in one of the many environments where erosion dominates, like slopes, coastal regions, riverbanks, or mountain edges, they would be wiped away before burial can occur. Even in stable depositional environments like deep ocean basins, the formation of future rock layers is uncertain. The ocean floor constantly changes. Sediments that settle there may eventually be carried to subduction zones and pulled back into the mantle. The chemicals within them would melt and mix with the Earth's interior. Any sign of human industry would vanish at that stage. Another signal is alterations to carbon cycles. Burning fossil fuels releases carbon into the atmosphere, changing carbon isotope ratios. These shifts do appear in sediments today, but they can resemble natural climate events from Earth's past. Without knowledge of modern human activity, distinguishing the cause of a particular isotope change becomes challenging. A future geologist might interpret the shift as a volcanic event or a natural methane release, unless very specific markers were present nearby. And even those markers could be destroyed by tectonic activity, erosion, or metamorphism long before they are discovered. Radioactive materials offer another possible signature, especially the isotopes produced by nuclear reactors and weapons. Some of these isotopes have long half-lives, but even they decay or disperse over time. After 1 million years, many of the isotopes that seem striking to us today would be faint or gone. Only a few, such as plutonium-244, might remain detectable. Yet their presence could still be interpreted as natural, because certain isotopes can form through rare astrophysical events that occur occasionally throughout Earth's history. Without context, even unusual isotopes do not prove the existence of a technological civilization. They only show that something altered the environment in a specific way. So when scientists ask what evidence survives 1 million years, the answer is subtle. Very little remains that is unmistakably artificial. Most materials transform, scatter, or dissolve. Most signals blend into natural patterns. Most structures vanish. And the things that do survive require extraordinary conditions. Burial in an anoxic environment, for example, can preserve organic molecules for extended periods. But those environments are rare. Rapid sedimentation helps too, as it protects items from biological degradation. Yet rapid sedimentation tends to occur in specific regions that shift over time. Even then, pressure and heat over millions of years gradually alter what's buried. It's also important to consider the rarity of finding any particular geological signal. Even if a small set of chemical markers from human activity remain detectable somewhere, they might be preserved in only a handful of places on Earth. Out of millions of square kilometers of land and ocean, the informative layer might exist only in narrow pockets. And finding those pockets would require drilling or sampling in the correct location. It's entirely possible that future explorers could miss the evidence by chance alone. This perspective applies equally to hypothetical civilizations of the distant past. If they existed briefly and in limited regions, their traces might never have been preserved. If their settlements were built near coasts or river deltas or lowlands, erosion would remove them. If they relied on materials that degrade rapidly, their artifacts would vanish. If they produced only minimal chemical alterations, those changes would blend into natural variations. The more we understand these processes, the clearer it becomes that the geological record is selective rather than complete. This does not imply that mysterious civilizations once existed. It only clarifies that geological preservation is not a guarantee. It is an exception. The Earth records only certain events, in certain materials under certain conditions. Everything else becomes part of the unrecorded past. One interesting comparison is what survives from ancient natural events. Volcanic eruptions leave ash layers, but those layers often erode away. Meteor impacts leave craters, but erosion can remove them too. Entire mountain ranges formed by collisions between continents have disappeared over time. Ancient river systems once crossed large regions but left almost no geological record. Even major shifts in climate sometimes leave minimal evidence, unless they coincide with rapid sedimentation or unusual chemical conditions. When natural events on these scales can vanish, it's clear why the traces of human activity or any brief industrial period might not endure. The planet does not intentionally preserve history. It simply follows physical processes, and those processes erase far more than they save. Understanding what evidence can survive 1 million years helps refine the kinds of questions scientists ask. Instead of looking for structures, they consider chemical markers. Instead of seeking intact objects, They search for deviations in natural cycles. Instead of expecting clear signs, they examine tiny anomalies that require careful interpretation. Even then, interpretation is complicated. Many natural processes mimic the signals we expect from artificial ones. Methane spikes can come from wetlands or permafrost, not industry. Carbon shifts might come from volcanic outgassing. Plastic-like materials can form naturally under certain conditions. Metallic deposits can result from hydrothermal vents. Without a complete picture, it becomes difficult to separate the artificial from the natural. This complexity is part of why the Silurian Hypothesis is framed cautiously. It doesn't argue that earlier civilizations existed. It focuses on whether we could detect them if they did. And the more we understand what survives deep time, the more balanced the question becomes. Not because the idea gains probability, but because the limitations of the geological record become clearer. Even today, within our own era, scientists occasionally discover evidence of natural events they didn't know occurred. New fossil beds appear in unexpected places. Ancient climate shifts become visible only after drilling into ice or rock. Entire species are identified from single fragments. All these discoveries show how much is still hidden, waiting to be uncovered by chance. The Earth keeps its history unevenly. Some moments are stored, others are swept away. 1,000,000 years is long enough to erase nearly everything humanity has built. Climate, in the geological sense, is less like a snapshot and more like a long record of shifting conditions written slowly into the planet itself. Unlike physical objects that break, crumble, dissolve or vanish over the course of thousands of years, climate leaves broader imprints. These imprints aren't obvious at first glance. You won't find them marked directly in a single rock or a single fossil. Instead, they emerge when scientists examine patterns across wide spans of sediment, chemical deposits, and preserved biological materials. It's through these large-scale patterns that we learn what Earth's environment was like millions of years ago. Trying to read those patterns is a bit like studying the faint residue left behind after an event, rather than the event itself. No one can see the climates of the Silurian, Jurassic, or Paleocene eras with their own eyes. But they can study the way certain elements appear in rock layers, how microfossils accumulate, how ancient soils formed, and how isotopes vary through thick sequences of sediment. Together, these small hints build a picture of temperature changes, atmospheric shifts, ocean chemistry, and global cycles. The value of climate clues becomes clearer when we consider how easily physical evidence of civilizations disappears. While buildings and tools might vanish within a short geological window, global climate disturbances linger far longer. They affect the entire planet. They seep into every environment. They alter chemical balances in oceans, soils, and the atmosphere. And because climate affects so many processes at once, its signatures often persist where other traces fade. That's why climate analysis plays a central role in discussions about the Silurian hypothesis. The hypothesis doesn't claim any ancient civilization existed. It asks whether, if one had, the climate record would allow us to detect unusual disturbances unlike those caused by natural cycles. To explore that question, you first have to understand what kinds of climate changes the Earth naturally undergoes, how large those changes can be, and how they appear in the geological record. As the planet moves through time, it experiences considerable variation in temperature and atmospheric composition. During some eras, Earth was warmer than anything we experience today. During others, ice sheets covered continents. Carbon dioxide levels have ranged from extremely high to very low. Oxygen levels have fluctuated dramatically. These shifts can occur gradually over millions of years or abruptly over thousands, sometimes even hundreds. Each type of shift leaves behind specific markers. For example, when global temperatures rise sharply, the ratio of carbon isotopes in sediments often changes. This is because large amounts of carbon enter the atmosphere and oceans, influencing how carbon atoms spread through living organisms dissolved minerals and sediments. When the planet cools, the reverse patterns may appear. Volcanic eruptions, which inject gases and ash into the environment, leave chemical signals of sulfur or certain trace metals. Meteor impacts leave residues of rare elements. Floods, droughts, and changes in vegetation all imprint themselves in various ways. Yet reading these clues isn't straightforward. They overlap, blur, and sometimes mimic each other. A carbon isotope spike might signal a volcanic event, a large release of methane from ocean deposits, or the burning of massive quantities of organic material. Without context, it's impossible to know which occurred. Context comes from studying multiple types of clues together. Scientists compare isotope data with fossil distributions, sediment thickness, mineral compositions, and other indicators to refine their interpretations. One of the most informative types of climate evidence comes from ancient marine sediments. Oceans cover most of the Earth, and for long stretches of time they accumulate fine particles that settle to the sea floor. Over millions of years, these layers become rock. The composition of each layer reflects conditions in the ocean at the time it formed. If temperatures rose, certain microorganisms became more abundant. If oxygen levels dropped, specific types of sediments accumulated. If carbon concentrations increased, the ratios in shells and organic materials changed. Even microscopic remains of tiny marine organisms carry climate information. This kind of record is detailed, but with limitations. The ocean floor is constantly being renewed by plate tectonics. The oldest seafloor preserved today is about 200 million years old. Anything older has been subducted and recycled. That means much of Earth's climate history, especially from its earlier eras, is missing from the seafloor record. Only sediments that accumulated on continental shelves and inland seas have a chance of surviving longer. Those areas offer windows into older climates, but they don't capture a full global picture. Even with these gaps, scientists have managed to reconstruct major climate events, including abrupt warming periods, rapid cooling events, glaciation cycles, ocean anoxia episodes, and mass extinction triggers. When seen together, these events reveal that Earth is capable of extreme shifts long before humans appeared. Some changes happen slowly, others unfold surprisingly fast. In every case, the rock record preserves only what happened to survive the combined forces of erosion, burial, and tectonic movement. When considering the possibility of a civilization influencing climate in the deep past, the key question becomes whether any artificial signal would be distinguishable from natural variations. Modern human activity, for example, leaves several distinct environmental fingerprints. The rapid release of carbon from fossil fuels alters carbon isotope ratios. Synthetic chemicals enter the environment and accumulate in certain areas. Plastics travel through oceans and sediments. Radioactive materials appear in measurable quantities. Agricultural practices modify soils. Even nitrogen cycles shift due to fertilizer use. Some of these signals are subtle, some are widespread, some might persist for a very long time under the right conditions. But the critical issue is not whether humans leave traces today, it is whether those traces would remain recognizable after 1 million years or longer. If a future species examined sediments from the modern era, what would they see? Carbon isotope changes might still be detectable, but carbon cycles have shifted many times throughout Earth's history. Volcanic events, methane releases, asteroid impacts, and natural climate transitions can all produce similar patterns. Without additional evidence, a future geologist might not interpret such a shift as artificial. Synthetic chemicals are less common in nature, but many degrade over time. Some might become trapped in deeply buried sediments. Others would decompose. Even if some survived, they would be present only in specific environments. If the sediment containing them eroded, the evidence would vanish. If it became metamorphosed by heat and pressure, the chemical signatures would change. Radioactive isotopes pose another challenge. They decay at known rates, and some would still exist in trace amounts after 1 million years. However, Natural processes also produce radioactive isotopes. The Earth contains uranium, thorium, and potassium, each of which undergoes radioactive decay. Meteor impacts introduce rare isotopes. Supernova debris has occasionally left measurable traces in Earth sediments. Distinguishing between natural and artificial sources would require context, and context is exactly what often disappears in geological time. Other markers, such as artificial metal concentrations, might seem more robust. Industrial activity redistributes metals like lead, copper, chromium, and nickel. These metals can appear in sediments where natural concentrations would normally be lower. But geological processes also move metals. Hydrothermal vents, volcanic eruptions, groundwater flows, and weathering can all alter metal distributions. Over millions of years, metals migrate, disperse, and reform in new minerals. Their original patterns may not survive in a recognizable way. This uncertainty highlights why climate records are both valuable and limited when searching for unusual events. On a broad scale, the climate record reveals major transitions. It shows when Earth warmed significantly, when oceans lost oxygen, when carbon levels rose sharply, and when plant and animal life changed. These transitions provide a framework for understanding how the planet responds to different forces, but they don't always reveal the exact cause of each change. For example, the Paleocene-Eocene thermal maximum left a strong signal in the geological record. Carbon isotope ratios shifted rapidly, temperatures increased, ocean chemistry changed, ecosystems transformed. But the precise trigger behind this event remains debated. Some suggest volcanic activity, others point to methane release, some propose orbital variations. There is no way to know with certainty, because the specific evidence of the cause did not survive. This illustrates a key point. Even dramatic global events leave behind records that require careful interpretation, and sometimes that interpretation remains uncertain even with many clues available. A smaller, shorter, or less widespread disturbance would be even harder to detect. If an industrial civilization existed in a limited region, or produced modest environmental impacts, the record might not preserve anything beyond traces that look natural. Some researchers studying the Silurian Hypothesis emphasize that any hypothetical civilization would have to be global and long-lasting to leave an unmistakable signature. Localized activity wouldn't be enough. Even a sizable population using industrial tools would likely leave only faint chemical disturbances unless they altered the planet's carbon cycles or produced large quantities of artificial compounds. And even then, the resulting markers could blend into natural patterns. Part of the challenge lies in how sediments accumulate. A thin layer recording a few thousand years might be all that remains of a long period of time. In some places, an entire million-year stretch might be preserved as only a few centimetres of rock. If that layer underwent erosion or metamorphism, it would vanish. Meanwhile, other regions might accumulate thick layers that do not capture changes occurring elsewhere. Climate events often vary in intensity by region, and a global disturbance might look minor if the preserved section happens to come from a place that was unaffected. This uneven recording means that to read the ancient climate for clues, scientists must compare wide ranges of samples from many locations. They have to compensate for what is missing and interpret what is present with care. The record is full of interruptions. Gaps can last hundreds of thousands or millions of years. Between two preserved layers, an entire climate event might have occurred and disappeared without leaving a trace. Thinking about all of this helps explain why the climate record cannot provide certainty about hypothetical ancient civilizations. It isn't because scientists lack tools, it's because the Earth doesn't hold on to everything. Climate shifts are one of the most persistent indicators we have, yet even they blur over long timescales. We can see patterns, but patterns alone don't reveal the cause with perfect clarity. Still, the climate record remains one of the strongest tools for studying Earth's ancient past. It shows us how dynamic the planet is. It reveals cycles of warming and cooling that occurred without any influence from intelligent life. It helps us understand how ecosystems respond to stress, and it occasionally offers hints of unexpected transitions that challenge our assumptions. These transitions invite questions without framing them as conclusions. They encourage scientists to look deeper, compare more data, refine models, and approach the past with humility. The climate record doesn't tell us everything, but it tells us enough to know that Earth has undergone enormous changes with or without help from any species. Some parts of Earth's history appear quiet not because nothing happened, but because almost nothing was preserved. This quietness is what many scientists call fossil silence, the long stretches of time where life certainly existed, yet left behind barely any record. When people imagine fossils, they often picture full skeletons displayed in museums or neatly preserved shells in rock layers. But these iconic examples are unusual. Fossilization depends on circumstances so specific that the vast majority of organisms never enter the record at all. For every fossil a scientist uncovers, countless life forms once lived and vanished without leaving the slightest trace. This silence is important when thinking about deep time. It reminds us that even major evolutionary developments can appear only faintly in the rocks. The idea of a complete fossil timeline is comforting because it gives the impression that we can trace life step by step. In reality, the record is made up of widely spaced snapshots, separated by enormous intervals where entire species, ecosystems and environmental transitions have no physical representation. If you start with the basics, fossilization is far from a guaranteed process. An organism must die in a location that promotes preservation. Most environments are not suitable. A creature dying on a forest floor is usually consumed by scavengers and decomposers. Soft tissues disappear quickly. Bones break or scatter. Weather damages whatever remains. Even in open plains, deserts or mountains, the conditions rarely support fossil formation. For fossilization to begin, rapid burial is essential. Sediments need to cover the body before it decomposes fully. That happens most often underwater, in lakes, rivers, or shallow seas where sediment accumulates steadily. Even then, the chemistry of the water and the type of sediment matter. Some environments preserve shells well but dissolve bones. Others preserve impressions but not hard parts. Because these conditions are rare, the fossil record naturally excludes most of what lived. Soft-bodied creatures almost never fossilize unless they settle into environments with low oxygen and fine sediments. Hard-shelled organisms fossilize more often, but even then, only a small percentage survive long enough to be preserved in rock. After fossilization, the specimen must avoid being eroded, crushed, melted, or chemically altered over millions of years. Only after surviving all that might it be exposed at the surface where a scientist can find it. The number of surviving fossils becomes a tiny fraction of the original organisms. This imbalance shows why fossil silence is common. For every species that appears in the record, there were many more that never did. Even whole communities might be missing. When scientists find new fossil beds, they often redefine what they thought about certain periods because the new discoveries represent types of organisms that were never previously known. These sudden additions don't mean the creatures appeared suddenly in the past. They simply mean the right conditions to preserve them happened in specific places, and those places were discovered. The fossil record also varies by region. Some continents contain rich collections of fossils from certain eras and almost none from others. Differences in erosion, sedimentation, and tectonic uplift determine what survives. In some periods, entire regions were covered by shallow seas that produced layered fossil-rich deposits. In other periods, vast land areas produced almost no fossils because the environment didn't favour preservation. These regional variations distort our understanding. For example, if fossils from a certain time period are abundant in one area but absent in another, it doesn't necessarily mean that the species were absent from the second region. It often means the conditions simply didn't preserve them there. When exploring the Silurian Hypothesis, these details matter. The question isn't whether a past civilization existed. The question is whether the absence of evidence carries enough weight to state confidently that it did not. The fossil record shows us that absence often means nothing more than a lack of preservation. If the planet can erase evidence of animal species that dominated ecosystems for millions of years, then the silence itself is not a robust argument against brief or localized events in deep time. Many people assume that fossils are plentiful and evenly distributed through the geological layers, but some periods contain barely any fossils at all. These gaps are not unusual, they occur throughout Earth's history. One particularly striking example is Romer's Gap, a roughly 10 million year interval in the early Carboniferous where tetrapod fossils are exceedingly rare. Scientists know that tetrapods existed during this time, but the rocks remain quiet. The gap likely formed because oxygen levels and environmental conditions limited fossil preservation. The animals lived, reproduced, evolved, and interacted, yet almost no traces remain today. There are other gaps. The earlier stages of vertebrate evolution appear scattered through fragmentary fossils. Entire branches of the evolutionary tree show up abruptly because earlier forms have poor preservation. Soft-bodied organisms from the early Cambrian are known largely from a few exceptional fossil sites. Without those rare locations, our understanding of early animal evolution would be drastically different. These examples show how much depends on the rare chance that conditions aligned just right. The same pattern holds for periods after mass extinctions. After the end Permian extinction, ecosystems took millions of years to recover. Fossils from this recovery phase are sparse. The intervals immediately after major global events often lack robust fossils because the environments were unstable, erosion was intense, and sedimentation patterns changed rapidly. These conditions create blank sections in the fossil timeline. Determining what these silent sections represent is a major challenge. Scientists must decide whether a gap means few organisms existed, or whether the organisms existed but left no evidence. Often, they rely on indirect hints. Chemical markers in rocks might reveal shifts in oxygen levels. Sediment structures might show changes in water flow. Tiny microfossils might indicate the presence of broader ecosystems. But direct evidence is still absent. The silence forces researchers to fill in missing information cautiously, knowing that conclusions are only as strong as the available fragments. Extending this idea into the framework of the Silurian Hypothesis, if a brief industrial civilization existed millions of years ago, it would be unlikely to leave recognizable fossils. Civilizations don't fossilize. Their remains depend on artifacts or altered landscapes, neither of which fossilize as easily as biological structures. Even with biological organisms, fossilization is rare. With technological materials, the odds become even lower. Most of the activities of humans today take place on land, and land-based fossilization is far less common than marine fossilization. Erosion destroys land features quickly. Rivers rework sediments. Mountain building buries entire regions. Ice sheets scour landscapes clean. Floodplains cycle between deposition and erosion. It becomes easy to see why fossil silence does not provide a reliable basis for eliminating hypothetical scenarios. But fossil silence tells us something else too. It shows that extinction and survival are often not preserved evenly. Some animals leave abundant fossils because they lived in environments favourable for preservation. Others lived in ecosystems that produced almost none. When interpreting the fossil record, scientists consider these preservation biases carefully. They avoid assuming that the absence of fossils from a certain region or time means the absence of life itself. They look for multiple lines of evidence to understand what may have happened. For example, scientists studying early mammals used to think that mammals were small, rare, and insignificant during the age of dinosaurs. Later discoveries contradicted this view. More fossil sites revealed that mammals were far more diverse and ecologically important than once believed. The earlier interpretation was based on fossil scarcity rather than actual biological rarity. This pattern has repeated throughout paleontology. New fossil discoveries disrupt old assumptions because the record is incomplete. When you apply this understanding to deeper geological layers, the uncertainties grow. The farther back in time you go, the worse the preservation becomes. Rocks older than about 500 million years contain extremely limited fossil evidence. Early multicellular life is known only from a few impressions. Before that, the record is dominated by chemical traces, stromatolites, and microfossils that require careful interpretation. Anything soft-bodied or delicate would not be preserved. Most of Earth's biological history is invisible. This invisibility creates a distinction between what fossil silence can tell us and what it cannot. It can reveal patterns of preservation. It can highlight the limitations of the record. It can show which environments favoured fossilization. It can demonstrate how often entire lineages appear, abruptly, with little prior record. But fossil silence cannot confirm that something never existed. It cannot eliminate possibilities based solely on lack of evidence. It cannot provide complete timelines for life's history. It cannot fill in missing stories. It cannot act as a perfect filter for unusual events in deep time. Even catastrophic events that dramatically altered ecosystems may leave little fossil evidence. The end-Triassic extinction, for instance, is known mainly through chemical and sedimentary markers. The fossil record around this time is sparse. Changes in species distributions are visible in some regions, but other regions preserve nothing. For paleontologists trying to interpret the event, the gaps are significant. They ask, did species disappear suddenly? Did they decline gradually? Did the environment collapse in multiple phases? The fossil silence leaves important questions open. In some eras, fossils exist only at specific sites. These sites become the primary windows into entire ecosystems. Without them, scientists would know far less. The Burgess Shale in Canada, the Chengjiang site in China, and the Solnhofen limestone in Germany are examples of rare places where conditions were perfect for preserving delicate organisms. If those places had not happened to form, entire groups of animals would be unknown today. Their absence from the fossil record would have shaped our understanding dramatically. Thinking about this helps frame why scientists take fossil silence seriously, not as an invitation to speculate, but as a reminder to stay cautious when interpreting deep time. The fossil record is extraordinary in what it reveals, but limited by what it cannot capture. The Silurian Hypothesis uses fossil silence not as evidence for ancient civilizations, but as a way to examine the reliability of the record itself. If so many biological events are missing, if so many evolutionary transitions appear abruptly, if so many environments fail to preserve anything, then fossil silence cannot be used as definitive proof against the possibility of short-lived, localized or modestly sized intelligent species in deep time. Again, this is not to say such species existed. It simply shows the boundaries of what fossils can and cannot reveal. Evidence of technology doesn't behave like evidence of biology, and that difference becomes clear once we look closely at the materials humans rely on today. While living things either fossilize or vanish, technological materials interact with the planet in their own ways. Some are durable for decades, some last centuries, some break down quickly, others transform into entirely new compounds. When scientists think about the possibility of detecting any form of industry in the geological record, they focus on these materials and the scars they might leave behind, not because they expect to find anything unusual from the distant past, but because the exercise helps reveal the limits of geological preservation. To start, think about the wide range of substances produced by modern industry. Metals are mined, refined, and shaped. Plastics are manufactured in enormous quantities. Synthetic compounds enter water and soil. Concrete forms the framework of cities. Combustion engines release chemicals into the atmosphere. Even the simple act of heating and cooling materials leaves signatures in the environment. All of this contributes to what geologists sometimes refer to as the Technosphere, the collection of human-made materials that blanket parts of the planet. The Technosphere is impressive by human standards, but fragile when viewed through the lens of geological time. On a timescale of 1 million years, very little of it would remain intact. The artifacts and structures would disappear first, the chemicals would disperse next, the metals would corrode and be reabsorbed into minerals, and the plastics would continue to fragment until even the fragments lose their structure. Eventually, almost everything would merge into the surrounding rock or soil. What's left behind is not technology itself, but whatever chemical or mineral leftovers manage to persist. This helps explain why researchers evaluating the Silurian Hypothesis concentrate on geochemical traces. If a technological species existed long before humans, the objects they produced would almost certainly have vanished. Even metals capable of enduring for centuries cannot withstand millions of years of weathering, burial and metamorphism. Iron rusts and dissolves, copper corrodes, aluminum oxidizes, alloys separate or transform. Under high pressure and temperature, even robust metal artifacts lose their identity. They become part of the rock. Concrete, which is often thought of as one of the more durable materials we produce, breaks down under natural processes as well. Water infiltrates it, minerals leach out, cracks expand. Entire structures crumble, leaving behind irregular deposits that could easily be mistaken for natural sedimentary features once enough time passes. 1 million years of tectonic movement would distort or destroy these deposits entirely. Glass, although hard and seemingly stable, is also vulnerable to chemical and mechanical change. It can be dissolved by slightly alkaline water, it can fracture into tiny shards, it can recrystallize under certain temperatures. Over geological spans, glass rarely preserves its original shape or smooth surfaces. Instead, it becomes a granular residue, mixing with sand, clays, or volcanic materials. Identifying it as artificial after such extensive alteration would be nearly impossible. The materials most likely to persist are compounds that mineralize under specific conditions. Some synthetic chemicals, if trapped before decomposition, can bind with sediments to form unusual mineral structures. Metals discarded or deposited into sediments might combine with surrounding elements to produce geochemical anomalies, regions where certain metals appear in concentrations higher than expected. Even so, these anomalies must survive erosion, metamorphism, and tectonic recycling. And survival alone is not enough. The anomaly has to be recognizable as artificial rather than natural, which requires distinctive patterns rather than random enrichments. This is one of the reasons scientists focus on large-scale patterns rather than individual objects when examining the geologic record. A single patch of metal-rich sediment can form from natural hydrothermal processes. A chemical spike can result from volcanic activity. A thin layer of unusual minerals can form from asteroid impacts. Without context, these features tell us little about their cause, but patterns spanning multiple regions with consistent signatures suggest larger environmental changes. Modern human activity creates several such patterns, though their persistence depends on many factors. For example, lead concentrations in certain sediments peaked during the 20th century due to industrial use. These concentrations are detectable today, but the long-term durability of such markers is uncertain. Lead can migrate through soils and rocks. Chemical reactions can alter or dilute it. Water movement can carry it away. Over millions of years, the signal might fade or become indistinguishable from natural variations. Another example involves platinum group elements released by catalytic converters. These elements accumulate in roadside sediments. They are rare in nature, so their presence today is striking. But rare does not mean permanent. In the future, those sediments might erode. The elements might disperse at such low levels that their artificial origin is impossible to determine. Geological processes can also concentrate these elements naturally near certain types of volcanic systems. Without preserved context, Differentiating natural from artificial signatures becomes complicated. The distribution of artificial radionuclides offers another illustration. Nuclear activity creates isotopes that do not occur naturally, or occur only in extremely small amounts. Some of these isotopes have long half-lives, making them potentially detectable far into the future. But the question is not whether the isotopes exist, it's whether they survive in stable environments. If they settle in an area destined for erosion, they won't last. If they sit on crust that will be subducted, they will melt and disappear. Even if they remain in a stable sedimentary basin, decay might reduce their signature to a level too faint to distinguish from natural background levels. Part of understanding mineral scars involves recognizing which materials resist geological processes best. The answer is surprisingly limited. Most artificial materials are chemically unstable over long spans. They degrade into simpler compounds that resemble natural components of rock or soil. Only a few might form novel minerals or unusual combinations. If those minerals persist, they could survive as tiny markers of technological activity. But even then, the markers would exist only where conditions were right. If a hypothetical technological civilization operated in a region that later underwent metamorphism, its mineral signals would alter. Metamorphic processes transform mineral compositions and structures. A signature that once existed could be erased. Conversely, a region that remained geologically stable might preserve subtle anomalies. Those anomalies, however, would be scattered across the surface and might never be found unless someone drilled in exactly the right spot. The challenge of recognition becomes especially clear when comparing technological minerals to natural ones. The Earth has countless ways of producing unusual mineral assemblages. Hydrothermal vents create metal-rich deposits. Volcanic eruptions produce glasses, ash layers, and complex minerals. Sediments can concentrate metals due to water movement. Pressure and heat can produce exotic crystalline structures. Even meteor impacts generate distinctive features like shocked quartz. For scientists to identify a mineral deposit as artificial, it must differ from natural processes in a clear and consistent way. This raises a key point. The markers of technology must be both durable and unique. Most human-made materials fail the durability test. Those that pass durability often fail uniqueness, because natural processes can produce similar patterns. The difficulty of distinguishing artificial from natural signals is one of the core reasons the Silurian hypothesis remains cautious. The point is not to suggest something existed, but to assess what would remain if something had existed. That assessment shows that the traces would be subtle and easy to misinterpret. Think, for example, of industrial mining. Human mining removes large quantities of material from the earth and concentrates certain elements elsewhere. These disturbances may alter the geochemical landscape in ways that do not resemble natural patterns, but mining pits fill in over time. Erosion redistributes materials, and tectonic activity can bury or distort mines. After long spans, only the concentrated metal deposits might remain, and even those may not appear artificial without intact context. Consider also the process of smelting metals. Smelting produces slag, a glassy byproduct rich in metals and minerals not commonly found together in nature. Today, slag heaps are noticeable features near historical industrial centres, but slag weathers rapidly when exposed. If buried, it can alter chemically. Over 1 million years, slag could either degrade entirely or transform into minerals that resemble volcanic glass or naturally fused materials. Its artificial origin becomes ambiguous. Even pigments and dyes used in modern materials might leave traces. Certain synthetic pigments contain rare metal combinations, but these pigments exist in minute quantities relative to the scale of geological processes. They disperse quickly and degrade chemically. Only under exceptional conditions might they survive in sediments, and even then they would appear as isolated chemical oddities rather than clear signs of technology. Understanding these limitations helps clarify why scientists often look at global-scale disruptions as a more realistic type of evidence. If a civilization reached widespread industrial capability, it might alter the atmosphere or oceans enough to leave persistent chemical signatures, but such signatures, as discussed earlier, can be difficult to distinguish from natural climate events without additional markers. One of the more persistent industrial effects is the redistribution of carbon. Burning fossil fuels releases carbon with a distinctive isotopic fingerprint. If this fingerprint becomes trapped in sediment layers, it could last for millions of years. But natural carbon shifts occur regularly across Earth's history. A future species finding a carbon anomaly would need context to interpret it. Without connecting markers, the spike might be attributed to volcanism, methane release, or other natural processes. The same challenge applies to nitrogen cycles influenced by fertilizers. Modern agriculture introduces nitrogen compounds into soils and waterways, altering natural nitrogen ratios. These shifts might leave signatures in sediments, but nitrogen is highly mobile chemically. Over millions of years, those signatures might diffuse, react, or dissolve into broader patterns. Distinguishing them from natural variations becomes uncertain. What this means for the Silurian hypothesis is straightforward and grounded in geological reality. The materials used by technological species degrade unless conditions lock them away early. The mineral and chemical scars they leave are often subtle, possibly ambiguous, and vulnerable to destruction. Even the processes most likely to persist, like the global redistribution of elements, can be confused with natural patterns unless the evidence is preserved with enough context. This perspective doesn't suggest that unknown civilizations existed in the deep past. It simply clarifies the challenge of detection. If the Earth erases structures, objects, and localized chemical anomalies within relatively short periods, then the search for unmistakable technological signatures becomes difficult. This difficulty does not indicate that there is something to find. It only reflects how active and dynamic the planet is. Thinking through these scenarios helps build a more accurate understanding of geological constraints. It provides a realistic view of how fragile technological evidence is, especially when compared to the massive ongoing processes shaping the crust. Large-scale extinction events have reshaped Earth's history repeatedly, leaving behind altered ecosystems, vacant niches, and reorganized environments. These events have their own rhythm, sometimes unfolding over millions of years, and sometimes happening in what amounts to geological moments. When looking at how these changes appear in the rock record, another dimension becomes clear. Mass extinctions don't only wipe out species, they also transform landscapes, bury entire regions in sediment, remodel coastlines, shift climate patterns, and alter ocean chemistry. All of these changes can play a role in erasing or overwriting evidence of anything that existed before them. This point becomes essential when scientists explore the limits of how long traces of civilization or industry could last. Mass extinctions aren't gentle transitions. They're disruptive events that strain Earth systems enough to cause widespread ecological collapse. During such events, sediments can accumulate rapidly, seas can expand or contract, volcanoes can erupt at rates far above normal levels, and erosion can accelerate. These processes don't just affect living organisms, they also affect the rocks their remains might have been preserved in. Thinking about mass extinctions in this way helps separate the popular image of catastrophic events from their actual geological significance. People often imagine an asteroid impact or volcanic eruption as a single destructive moment, but the geological aftermath is what matters most. It's the aftermath that decides which evidence endures and which disappears. If human cities existed during any of these periods, the global environmental changes would reshape the terrain around them so thoroughly that even the most persistent materials would be vulnerable to destruction. To understand how this works, it helps to look back at the extinctions themselves. The end Permian extinction was the most severe known, eliminating the majority of species both on land and in the oceans. Yet the event's cause, and the detailed sequence of changes surrounding it, is still debated because the evidence is uneven. In some regions, thick sediment layers capture the transition. In others, erosion removed the relevant rocks entirely. Even though the extinction happened on a global scale, the record is incomplete. This shows how easily major events can erase earlier layers. During the end Permian, enormous volcanic activity produced vast lava flows and released large quantities of gases into the atmosphere. These gases altered climate, ocean chemistry, and biological communities. The volcanic deposits themselves covered huge areas in thick basalt layers. If any geological features or structures existed on the land before these eruptions, they would have been buried beneath molten rock. Later erosion would cycle those rocks, exposing them again only after considerable alteration. Very few details from the pre-eruption landscape remain clear today. The Triassic-Jurassic extinction, another large event, reshaped ecosystems as well. During this extinction, volcanic outgassing likely triggered climate changes that affected global temperatures and atmospheric composition. The sediments from this period show that many regions experienced altered environments, shifting coastlines, and fluctuating sea levels. These transitions often make it difficult to isolate clear and continuous fossil sequences. As with other extinctions, the geological disturbances blur the traces of what came before. If we consider the Cretaceous-Paleogene event, known for the asteroid that contributed to the demise of non-avian dinosaurs, we see both dramatic destruction and varied preservation. The impact created layers rich in elements rarely found on Earth's surface. These layers survived because they settled quickly across broad regions, but the impact also caused wildfires, tsunamis, earthquakes, and immense sediment rearrangement. Areas close to the impact zone were transformed almost instantly. Whatever structures or surfaces existed beforehand were overwhelmed by deposition, shock waves, and geological mixing. In other areas, erosion removed layers entirely. The result is a patchwork record. Thinking about how these events transform the landscape helps clarify what they could erase. Structures built by humans today could not endure global environmental disturbances on this scale. Earthquakes would collapse buildings, fires would spread across regions, flooding would bury communities in sediment, tsunamis would carry debris far from its original location, volcanic ash could blanket entire cities, and once the immediate chaotic phase ended, the planet would go on altering the terrain gradually. Newly deposited sediments would harden, erosion would redistribute materials, tectonic forces would shift everything again in the long run. This cycle of destruction and reformation ties directly into the Silurian Hypothesis. It shows that even if a civilization had reached an industrial stage millions of years ago, the odds of its structures surviving a mass extinction event are minimal. But beyond structures, the question becomes whether any indirect traces would persist. During mass extinctions, one of the most prominent geological features is rapid sedimentation. Large volumes of material accumulate quickly, often burying what lies beneath. Rapid burial is ideal for preserving fossils under some circumstances, but not for preserving artifacts or large structures. Technological materials degrade quickly compared to biological remains. Even if buried, their long-term stability is uncertain. Concrete deteriorates, metals oxidize or transform, plastics fragment, electronic components break down. A thick layer of ash or sediment could preserve outlines briefly, but over geological spans the original features would vanish. The ocean plays an important role as well. Many mass extinctions involve changes in sea level. Rising seas inundate coastlines and flood large regions. For human settlements, this would mean submergence. If the sea covered cities rapidly, the structures might collapse and scatter. If covered slowly, erosion and chemical dissolution would take place over time. Once underwater, the combination of biological activity and chemical interactions would accelerate decay. Long before the sediments of the new seabed hardened into rock, most artificial materials would be gone. Ocean anoxia, periods where parts of the ocean become depleted in oxygen, is another effect commonly associated with mass extinctions. These zones preserve organic matter well, but technological materials would not benefit in the same way. Organic remains do well in low oxygen environments, but industrial materials depend on chemical stability. Metals would still corrode. Plastics would still fragment, though more slowly. Without an unusual sequence of conditions, those materials would not endure deep time intact. Volcanism presents another mechanism through which evidence could be erased. Mass extinctions often coincide with increased volcanic activity, producing flows of lava and volcanic ash that cover wide areas. Lava destroys everything in its path and entombs whatever lies beneath. Ash and pyroclastic flows can bury regions in layers thick enough to collapse structures. Over time, heat and pressure lithify these layers, turning them into rock. Any artificial material within them may either melt, dissolve, or become altered beyond recognition. Minerals form at high temperatures that could mimic or overwrite technological signatures. In addition to these physical transformations, mass extinctions reshape ecosystems. The disappearance of species disrupts food webs and alters vegetation patterns. These changes affect erosion rates and sediment deposition. For instance, when plant life declines sharply, soils erode more easily. Increased erosion moves vast amounts of sediment from land to water. This process can bury or destroy whatever lies in its path. Once vegetation regrows, new landscapes form that bear little resemblance to the ones that existed before the extinction. The idea that a mass extinction could erase the traces of a civilization becomes even clearer when considering the timescales involved. Geological processes continue long after the extinction event itself. Following the initial upheaval, Earth requires millions of years to stabilize and rebuild ecosystems. During this period, landscapes change dramatically. Rivers carve new channels, mountains rise or fall, coastlines shift, tectonic plates continue their slow motions, entire regions may sink or be uplifted. If any artifacts remained after the initial destruction, they would likely not survive these continued changes. Another point worth noting is that ancient mass extinctions left behind only partial records themselves. Even though the extinction events are large enough to affect Earth on a global scale, our understanding of them remains incomplete because the rocks that should contain details are unevenly preserved. Some records are excellent, others are entirely absent. If something as monumental as the Permian event leaves an inconsistent record, then the traces of a short-lived industrial civilization would be far more difficult to identify. Some scientists use this line of reasoning to illustrate why mass extinctions cannot be used to argue that civilizations didn't exist. The rock record might not preserve everything, especially if environmental disturbances actively removed previous layers. Once sediments or structures are destroyed during the upheaval, the underlying evidence is gone permanently. Looking at the fossil record of these events reinforces the point. After each extinction, the re-emergence of life is visible, but the details of what existed immediately before are sometimes fragmentary. The fossil layers show a sudden shift in species, but the transition zones often contain only hints. Many species that lived before the extinction are known from a few scattered fossils, and the details of their decline remain unclear. This demonstrates how even biological evidence can be incomplete. Fossils record only what had the right conditions to preserve them. Anything that lived in the wrong environment at the wrong time left no trace. If living organisms disappear from the record so easily, technological artifacts, which are far less stable, would vanish even faster. One subtle but revealing observation from studying mass extinctions is how uniform some of the resulting sediment layers are. During certain extinction events, the same types of sediments appear across wide regions. This uniformity suggests widespread disruption. For example, dark, organic, rich shale layers show up in several extinctions. These shales indicate low oxygen conditions in the oceans. If large-scale technological activity occurred before such an event, the sediment layers that followed would likely bury the associated signals beneath uniform deposits. The distinctive details might be lost under the overwhelming volume of new material. These observations also highlight how mass extinctions complicate interpretations of ancient anomalies. When scientists see an unusual chemical spike or an unexpected mineral deposit in rocks, they typically consider natural explanations first. This is because mass extinctions coincide with environmental anomalies that might mimic artificial signals. Distinguishing between a natural carbon spike and one caused by industry becomes challenging if the context has been removed by later upheaval. Without multiple lines of supporting evidence, conclusions remain tentative. This doesn't imply that anything artificial occurred in Earth's distant past, but it shows that the record cannot always eliminate possibilities with certainty. Mass extinctions reset the surface of the planet repeatedly. Each event erases countless details and reshapes the material record. When trying to account for why certain things don't appear in the rocks, acknowledging the destructive power of these events provides a grounded explanation. Every time a scientist uncovers a fragment from Earth's past, whether it's a fossil, a mineral layer, or a subtle chemical marker, that discovery exists alongside a much larger story that remains mostly untold. The planet has existed for billions of years, but the portion of its story preserved in accessible form is limited. What we have are pieces that survived by chance. What we lack are the vast stretches of time where environments didn't favour preservation, where rocks were destroyed or buried too deeply, where ecosystems thrived yet left nothing behind. These unwritten histories form a quiet backdrop to everything we think we understand about Earth. This isn't a flaw in science. It's a reflection of how the planet works. Earth is constantly altering itself, and in doing so it edits its own record. When researchers discuss the Silurian Hypothesis, the idea isn't centered on speculation. Instead, it's built on the recognition that the planet's record-keeping is inherently incomplete. Whenever we look at a rock layer or a fossil bed, we're seeing what happened to survive, not the full list of what once existed. This understanding becomes a lesson in humility. It encourages scientists to approach deep time with caution, knowing how much remains invisible. One of the clearest examples of this comes from periods where entire landscapes disappeared through geological processes. Continents shift, mountain ranges rise and erode, oceans open and close. These movements swallow evidence. A continent that existed in one form hundreds of millions of years ago can look completely different today. In some cases, the land that once supported thriving ecosystems no longer exists at the surface at all. It has been folded, compressed, or melted into entirely new rock. Whatever lived or occurred in those older worlds is gone, unless a rare set of conditions preserved a trace. This reveals an important point about how science uses the available evidence. Researchers don't treat gaps as empty space, they treat them as missing information. When a fossil lineage appears suddenly, scientists know the species didn't emerge instantly. They infer that earlier forms lived in places that didn't fossilize well, or that existing fossils have not yet been found. This is part of the scientific process, recognizing the difference between a true absence and a lack of preservation. When examining Earth's unwritten histories, one recurring lesson is that preservation is selective. Soft-bodied species almost never enter the record unless buried in unusual environments. Organisms living in forests, mountains, or dry regions rarely fossilize. Shallow seas preserve more than land, but even then, the record depends on how quickly sediments accumulate. A species that existed for millions of years may be represented by only a handful of specimens. That limitation shapes our understanding of biological evolution. It reminds us that the fossil record isn't a diary. It's a series of scattered notes. The same principle applies to climate histories. Scientists use proxies like isotopes, pollen grains, tiny shells, and sediment composition to reconstruct temperatures, precipitation patterns, and atmospheric compositions. But the climate record is uneven. Some intervals are well preserved in deep-sea sediments or ice cores. Others are poorly captured or missing entirely. When the planet warms or cools abruptly, the changes may appear clearly in certain regions, but faintly, or not at all in others. Reconstructing global events requires combining incomplete datasets into coherent interpretations. Earth's unwritten histories extend beyond biological and climatic information. They also include geological processes that occurred on timescales too long for human experience to grasp intuitively. For example, entire volcanic provinces formed over millions of years, leaving thick basalt layers behind. These layers tell us something happened, but they don't capture the full picture. The conditions leading to those eruptions, the exact sequence of events, and the environmental impacts often remain uncertain. Even when clues survive, they represent only the end product, not the detailed chain of causes. This partial preservation teaches scientists to avoid assuming that the accessible portion of the record is representative of everything that ever occurred. It's a reminder to approach interpretations carefully. When an unusual chemical spike appears in sediments, the origin may be ambiguous. When a mass extinction shows sudden ecological change, the underlying causes may not be fully preserved. When species appear or disappear abruptly, the transitions may be artifacts of the limited record rather than truly instantaneous events. These uncertainties don't undermine science. Instead, they make the scientific process stronger by reinforcing the importance of multiple lines of evidence. Researchers compare fossils, sediments, isotopes, mineralogy, and atmospheric models to build a narrative that accounts for missing information. The past becomes clearer not because any single piece is definitive, but because the combination of many partial clues leads to patterns that hold up under scrutiny. One practical lesson from these unwritten histories is understanding how rare it is for anything to be preserved. This context becomes especially relevant when considering whether evidence of an industrial civilization could survive deep time. The goal is not to argue that such civilizations existed, but to evaluate whether the absence of evidence is meaningful. Knowing how easily entire ecosystems vanish from the record helps frame the limits of geological detection. Another lesson comes from studying extinction events. These events often mark boundaries between geological periods, yet the details of the transitions remain sparse. For instance, the end Permian extinction is associated with widespread volcanic activity and global environmental stress. But the record is uneven enough that even basic questions remain open. Did the extinction unfold suddenly or gradually? Were multiple crises layered together? How did changes in ocean chemistry progress? The rock record preserves enough to show a catastrophe occurred, but not enough to explain everything about it. This selective visibility becomes even more pronounced when looking at the earliest periods of Earth's history. The first 2 billion years are recorded mainly through ancient minerals, metamorphosed rocks, and chemical residues. Nearly all direct evidence of early life is missing. Researchers must infer biological activity through isotopic patterns and stromatolite structures. These faint signals reveal that life existed early, but they do not reveal the diversity, complexity, or behaviours of those organisms. Something similar happens when studying ancient ocean chemistry. Geological layers indicate episodes when the oceans became oxygen poor or rich in certain metals. But the nuances of these events, the exact triggers, the feedback loops, the regional differences, remain largely hidden. Scientists rely on models to fill in the gaps, knowing that the preserved signals represent broad strokes, not fine detail. Yet despite these limitations, science steadily refines its understanding. New fossils appear in unexpected places. Drilling projects retrieve samples from deeper layers. Chemical analysis techniques improve. Even though the planet preserves only fragments, each fragment contains information waiting to be interpreted. The process resembles reconstructing a story from a set of surviving pages rather than a complete book. The narrative is built carefully, with open acknowledgement of what's known, what's uncertain, and what's missing. This approach provides a framework for examining questions like those raised by the Silurian Hypothesis. The hypothesis doesn't claim ancient civilizations existed. It examines the conditions required for the record to show them if they did. That examination reveals that the record is far from comprehensive. Even major geological events leave behind incomplete traces. The absence of clear evidence, therefore, cannot conclusively eliminate hypothetical possibilities. Instead, it highlights the practical constraints imposed by deep time. Looking at Earth's unwritten histories teaches another important lesson. Evidence can be regional, and global events can look local if the preserved layers come only from specific environments. A single sediment core may show a carbon spike, another may not. One fossil bed may capture species diversity, another may miss entire groups. The planet does not distribute information evenly. If a technological species existed only in certain regions or produced only modest environmental impacts, the surviving evidence might be minimal or absent. This is not an argument for hidden civilizations. It's a recognition that our confidence in interpreting deep time must always account for preservation biases. Scientists regularly revise their understanding of ancient eras when new evidence emerges. The field remains dynamic because the planet reveals information slowly and unpredictably. These unwritten histories also underscore how changeable Earth is. Landscapes appear permanent to humans, but they transform continually. River systems shift, deltas grow and shrink, coastlines migrate, glaciers advance and retreat. Wind and water carve new landforms. Volcanic eruptions build mountains that later erode to plains. These changes influence what becomes preserved. A region might hold abundant evidence during one era, but lose that evidence entirely in the next. Understanding these shifts encourages a more flexible interpretation of deep time. It suggests that researchers must remain open to revising ideas when new pieces of the puzzle come to light. The scientific method thrives on this openness. Another lesson emerges from the contrast between what is preserved and what is lost. Occasionally, scientists discover fossil sites so rare that they alter entire fields of study. A single deposit can reveal species previously unknown, ecological interactions never considered, or behaviours inferred from exceptional preservation. These sites serve as reminders of how much might still lie hidden. If such discoveries can reshape our understanding of well-studied eras, then the scope of what remains unseen in older, less complete periods becomes even more significant. All of these insights reinforce the idea that Earth's record is not a complete archive. It is a selective sampler of past worlds. The unwritten portions are equally influential in shaping how we interpret the written ones. The gaps guide scientific caution. They encourage researchers to frame conclusions in terms of probability rather than certainty. They remind us that deep time contains more than the rocks reveal. Speculation about intelligence often starts with the assumption that humans represent a single, unique outcome of evolution, one that arose once and only once. But that assumption is more a reflection of our limited perspective than a conclusion drawn from the broader story of life on Earth. When scientists look across millions of years of evolution, patterns of repeated innovation appear everywhere. Eyes evolved independently in multiple groups. Wings appeared separately in insects, birds, and bats. Complex social structures emerged in ants, termites, and mammals. These repeated examples show that evolution doesn't always rely on a single path. Instead, it tends to explore certain solutions repeatedly when environments encourage similar pressures. Thinking about intelligence through that lens makes it natural to ask whether advanced cognition could have arisen more than once in Earth's long history. One reason this question becomes interesting is that intelligence, even in a broad sense, has appeared independently in several lineages. Cephalopods like octopuses and cuttlefish display problem-solving skills, tool use, and complex communication. Birds, particularly corvids and parrots, demonstrate advanced planning and memory abilities. Marine mammals show sophisticated social structures and cooperative hunting strategies. Primates, of course, stand out for their cognitive depth. None of these groups share a recent common ancestor with high intelligence. The similarities emerge through convergent evolution, where unrelated species develop comparable traits because they face similar challenges and opportunities. Convergent evolution invites a wider consideration of what might be possible across hundreds of millions of years. If environmental pressures repeatedly favour the development of complex brains, then intelligence may be less rare than we tend to imagine. The fossil record shows that ecosystems have cycled through many phases, with different dominant species taking the lead. Some eras favoured small, agile animals, others favoured large predators, still others favoured creatures adapted to extreme environments. It's reasonable to wonder whether some periods favoured cognitive complexity in ways that left little visible trace today. When scientists study the evolutionary history of intelligence, they often focus on the specific conditions that allowed human cognition to expand so dramatically. These include social interactions, environmental variability, tool use, language development, and dietary shifts. But similar conditions have existed many times in Earth's past. Changing climates, fluctuating food sources, complex ecosystems, and diverse species interactions have all occurred repeatedly. Each of these could theoretically create openings for intelligence to develop in different forms. Thinking about ancient Earth raises important considerations. The planet once hosted species that are now entirely gone, with no close modern relatives to hint at their cognitive abilities. Early synapsids, the ancestors of mammals, displayed a range of characteristics we associate with warm-blooded animals today, including potentially complex behaviours. Some theropod dinosaurs, especially maniraptorans, showed brain-to-body ratios approaching those of modern birds. Crocodilian ancestors and other archosaurs displayed social behaviour far more intricate than many people assume based on their modern descendants. Yet even with these hints, assessing cognitive potential from fossils alone is extremely difficult. Brain tissue does not fossilise. Researchers rely on endocasts, impressions of the interior skull cavity, to estimate brain size and structure. But brain size alone doesn't determine intelligence. Many animals with large brains are not capable of advanced cognition. Conversely, some highly intelligent species have relatively small brains. What matters is neural architecture, density, and how different brain regions interact. These qualities rarely leave clear traces in fossils. This limitation makes it difficult to know how many lineages approached high intelligence in the past. It also means that the absence of evidence isn't necessarily meaningful. Many species from the deep past are known only from fragmentary remains. Behavioural complexity, which plays an essential role in assessing intelligence, is almost always invisible. A species could have developed intricate social structures, complex communication methods, or advanced problem-solving abilities without leaving direct physical clues. Consider the case of birds. Modern corvids rival primates in cognitive ability, yet their ancestors appear in the fossil record mainly as bones that reveal little about their behavioural traits. If modern corvids went extinct and millions of years passed before another species reached similar intelligence, the fossil record would not reflect the complexity of the earlier group. Their intelligence would be an unwritten chapter. The same applies to cephalopods. They leave behind shells or beaks in some cases, but not the neural structures or behaviours that make them remarkable. If octopuses went extinct tomorrow, their intelligence would leave almost no trace in the geological record. Looking at prehistoric eras, the problem becomes even greater. Entire clades existed that have no modern equivalents. Many of these groups went extinct long before mammals became dominant. They may have had capacities we cannot evaluate, simply because no comparable animals exist today. Paleontologists must reconstruct their lives from bones, teeth, tracks, and sediments. These clues reveal locomotion, diet, environment, and sometimes reproductive strategies, but not cognition. Intelligence could have evolved in forms we would fail to recognize from the surviving evidence. The possibility of parallel minds in Earth's history becomes even more interesting when considering how many evolutionary experiments occurred during times of ecological stability. For example, during the early Mesozoic, ecosystems were open enough to allow new forms to thrive, but stable enough to permit long-term evolutionary refinement. Some theropods developed sophisticated sensory systems, potentially supporting advanced behaviour. The fossil record shows evidence of parental care, pack hunting, and complex social interactions among certain dinosaurs. While none of these behaviours prove high intelligence, they demonstrate the potential for cognitive growth given sufficient time and selective pressure. Another intriguing period is the Devonian, often called the Age of Fishes. This era saw rapid diversification among early vertebrates. Several groups developed advanced sensory capabilities. Some experimented with limb-like fins and early forms of terrestrial movement. While most Devonian species lacked characteristics associated with intelligence today, the sheer diversity of ecological roles suggests that complex behaviours likely existed. Yet the fossils reveal little about cognition, because soft tissues and behaviours leave almost no trace in rocks more than 300 million years old. The same issue applies to early synapsids, which thrived long before dinosaurs dominated the land. Some of these creatures displayed traits that hinted advanced behaviour: varied dentition, evidence of warm-bloodedness, potential fur, and complex movement patterns. They occupied ecological roles similar to modern mammals in certain respects. Intelligence may not have evolved in these groups, but the conditions supporting such evolution were present. If any species developed cognitive abilities more advanced than their contemporaries, the record would be too fragmentary to reveal it clearly. One of the lessons from Earth's unwritten histories is that potential does not guarantee outcome. Intelligence is not the inevitable endpoint of evolution. Many species succeed through strategies that do not require high cognition. Some thrive by reproducing rapidly. Others rely on specialized physical traits. Still others depend on chemical defenses, camouflage, or social cooperation without the need for advanced reasoning. Evolution explores many pathways simultaneously, and only a few lead to sophisticated intelligence. But given the vast time available, the question becomes not whether intelligence is inevitable, but whether it is possible more than once. If intelligence emerged independently in modern groups like cephalopods and birds, then the underlying mechanisms must have been accessible at different times in different lineages. Those mechanisms could have appeared in the deep past, only to vanish once the species carrying them went extinct. Without structural remains, those cognitive experiments would leave no geological signature. Another layer to consider involves environmental stability. Intelligence often develops in environments that are complex but not extreme. Too much unpredictability can hinder the development of advanced cognition, because species must prioritize survival over exploration. Too little unpredictability reduces pressure to innovate. The sweet spot between these conditions likely occurred multiple times across Earth's history. During such periods, species with advanced social structures or flexible behaviours might have gained advantages. Environmental transitions such as shifts from wet to dry climates or from forest to open grasslands can also promote intelligence. These transitions appeared repeatedly across different geological eras. Whenever ecosystems reorganized, some species adapted by developing more sophisticated ways of interacting with their surroundings. Many of the traits we associate with intelligence, tool use, social learning, planning and communication, are forms of behavioral flexibility. Flexibility becomes important in changing environments. If flexible, behaviorally complex species existed in earlier eras, they could have explored forms of intelligence comparable to, though not identical to, those seen in modern animals. Their abilities might not have reached the level of building tools or altering landscapes, but they could still represent advanced cognition relative to their contemporaries. These species would be nearly invisible in the fossil record. Considering parallel minds in Earth's history doesn't automatically connect to technological civilizations. intelligence does not guarantee technological development. Dolphins, octopuses, and birds show that advanced cognition can appear without leading to tool-based industry. Many intelligent species do not manipulate their environments in ways that leave durable geological traces. This distinction is central to evaluating possibilities within deep time. If a highly intelligent species existed millions of years ago, but did not develop widespread technology, the geological record would not reveal them. Their bones would be indistinguishable from those of less intelligent species. Their behaviors, communication methods, and social structures would leave no imprint. Intelligence could have emerged and vanished repeatedly without leaving any physical sign we could detect today. This perspective provides a more balanced way to examine the Silurian hypothesis. The hypothesis focuses on industrial civilizations, not on intelligence in general. But thinking about how intelligence evolves emphasizes how much of Earth's cognitive history may be hidden. The visible record shows only species with skeletal structures, robust enough to fossilize, and behaviors that can be inferred indirectly. Everything else remains speculative but plausible within the constraints of what we know. Parallel evolution of intelligence is not merely a theoretical exercise. It shows how evolution responds to similar challenges in similar ways. It reveals that intelligence is one of many potential strategies life can pursue, and that its appearance depends on ecological pressures rather than inevitability. Across hundreds of millions of years, conditions supporting cognitive growth likely appeared many times. This idea becomes more meaningful when we consider what comes next in our exploration. If intelligence could arise independently on multiple occasions, then our understanding of its development must include a broader view of Earth's evolutionary potential. That broader view naturally leads to the next question. If cognitive complexity may have emerged more than once, what might those earlier minds have looked like? And how would scientists search for traces of them when the record they could leave behind would be so fragile, so sparse, and so easily overwritten by the enormous processes that shape the planet over geological time? Trying to imagine earlier intelligent species on Earth requires setting aside the familiar reference points that shape how we think about cognition today. Humans tend to assume intelligence must resemble our own, not out of arrogance, but simply because our species is the only example of technological intelligence we can observe directly. Yet when researchers think about the possibility of earlier cognitive lineages, they avoid relying on human traits as the only template. Instead, they look at broader evolutionary patterns, ecological opportunities, and the kinds of anatomical and behavioral traits that signal the potential for advanced cognition. This approach does not assume such species existed. It simply works through the question logically, using what is known about the history of life and the environments that supported complexity at different times. To begin, it helps to notice that intelligence is not tied to any single body shape, metabolic strategy, or habitat. Evolution has produced clever animals in oceans, forests, deserts, and skies. Intelligence has emerged in vertebrates and invertebrates, warm-blooded species and cold-blooded ones, solitary hunters and social cooperators. If cognition depends on ecological pressure more than lineage, then many ancient groups could potentially develop advanced mental traits, given enough time and stability. The challenge is not identifying which species actually did, but identifying which species could have under the right circumstances. Looking back through geological time, one of the earliest possibilities involves the Devonian and Carboniferous periods, when early tetrapods and advanced fish explored environments that were newly available and highly dynamic. The ecosystems of this era were rich, diverse, and evolving quickly. Some species developed sensory systems more complex than anything seen before. Others experimented with limb-like structures or novel ways of navigating their environment. While there is no direct evidence of intelligence on the level of modern mammals or birds, the ecological complexity was there. If any group began exploring behaviours we might consider cognitively advanced, the fossil record would not show it clearly. Skeletons alone rarely reveal hints of behaviour, and the preservation of neural structures is virtually non-existent. Another possibility lies with the synapsids, especially in the periods before dinosaurs dominated. These early relatives of mammals displayed a range of traits that could support cognitive complexity. They had varied teeth, suggesting diverse diets and flexible behaviours. Their limb structures point toward active lifestyles. Some may have been warm-blooded or partially warm-blooded, which is often associated with higher metabolic demands and the potential for larger, more capable brains. These animals existed for millions of years, long enough for evolutionary experiments to play out. Yet their fossil record is limited in many regions, and most of their soft tissues and behaviours remain unknown. If an ancient lineage of synapsids reached cognitive levels far above their contemporaries, those signs would be nearly impossible to detect today. Moving forward through time brings us to the archosaurs, the group that includes crocodilians, pterosaurs and dinosaurs. Certain branches of this group display characteristics linked to social behaviour and sensory sophistication. Fossilised nesting sites show evidence of group activities. Trackways reveal coordinated movement patterns that may indicate pack behaviour. Some species cared for their young, others communicated through vocalizations enabled by specialised air sacs and resonant chambers. Brain cavity studies suggest that several theropod dinosaurs, particularly those closely related to birds, possessed relatively large brains with structures hinting at potential cognitive abilities. If we picture an alternate evolutionary path where a line of maniraptoran dinosaurs continued to grow increasingly intelligent, we can imagine behaviours far more complex than anything preserved in fossils. These animals might have used advanced communication, social learning, or problem solving. They could have passed knowledge across generations, yet none of these behaviours fossilise. Long after their extinction, we would see only bones and trackways. Their intelligence, if it had reached unusual heights, would not appear in the rock record unless it manifested in ways that left durable material traces. And even then, those traces would need to survive millions of years of erosion, burial, and tectonic activity. Another group worth considering is the pterosaurs, not because they show direct signs of advanced intelligence, but because flight demands a particular set of sensory and neurological adaptations. Pterosaurs possessed excellent vision, agile flight control, and in some cases surprisingly large brain regions dedicated to balance and coordination. Their ecological roles varied widely. Some were fish eaters, others were scavengers or insect hunters. A few grew to enormous sizes. Their brains, while not comparable to modern corvids or parrots, displayed patterns that could theoretically support complex behaviours. If a particular branch of pterosaurs began experimenting with advanced cognition, the fossil record would not capture it with precision. Another avenue for speculation comes from the marine environment. Cephalopods provide a living example of how intelligence can evolve independently in the oceans. In deep time, ammonites and belemnites, distant cephalopod relatives, thrived for hundreds of millions of years. These creatures had complex eyes, intricate shells, and advanced buoyancy control. Their closest modern equivalents, such as octopuses and squid, exhibit remarkable problem-solving abilities. If ancient cephalopods experimented with higher forms of cognition, the evidence would be hidden. Soft bodies leave almost no trace, and behaviours leave none at all. If a highly intelligent lineage rose and fell entirely within the oceans, the chances of preservation are vanishingly small. Another possibility involves the early mammals that existed during the Mesozoic. These mammals lived in the shadow of dinosaurs, evolving in diverse forms that included gliders, burrowers, insectivores, swimmers, and climbers. Some early mammals developed advanced hearing, tactile sensitivity, and nocturnal behaviours. These features often correlate with the potential for cognitive development. After the extinction of non-avian dinosaurs, mammals diversified rapidly. But the pre-extinction mammals also existed in complex ecosystems that could, under certain conditions, favour mental sophistication. If any early mammal lineage reached unusual cognitive levels but failed to survive into later periods, the evidence would be minimal. Their small size and delicate bones reduce fossilization chances. Their behaviours would be completely invisible in the record. Asking who might have been first is not the same as claiming any of these groups reached high intelligence. Instead, it highlights how many plausible evolutionary pathways existed. Across hundreds of millions of years, many groups possess the raw ingredients for complex cognition, social interactions, sensory refinement, long lifespans, environmental challenges, and ecological opportunities. At the same time, intelligence alone does not lead to technology. Among modern animals, dolphins and whales display extraordinary social structures and communication abilities, yet they do not create tools or manipulate the environment in ways that leave durable traces. Corvids and parrots understand cause and effect, use tools, and solve complex puzzles, yet their impact on the landscape is minimal. Octopuses demonstrate advanced learning, but lack long lifespans and stable social structures that might lead to cumulative knowledge. These examples show that a species can be highly intelligent without developing anything that would survive deep time. Therefore, if an ancient species evolved intelligence equivalent to or even exceeding that of modern dolphins or corvids, the geological record would reveal nothing of their cognitive capabilities. Their bones would look unremarkable. Their tools, if made from organic materials, would disappear quickly. Their behaviours, no matter how advanced, would vanish without trace. This leads to another important consideration. Intelligence could have appeared in forms that differ significantly from human intelligence. Humans tend to equate intelligence with problem-solving, tool use, symbolic language, and construction. But cognition can manifest in many ways. Social intelligence, emotional intelligence, ecological awareness, and navigation abilities are all forms of cognition. Some species might excel in areas humans overlook. An ancient species could have possessed complex communication or social organization without ever manipulating the physical environment in ways detectable millions of years later. Exploring the idea further means acknowledging how limited our perspective is. For example, some extinct species show hints of complex behavior through fossils of group nesting sites or coordinated trackways. Yet behavioral inference is always cautious. A trackway can show animals moving together, but it cannot reveal communication or planning. A nesting site can show parental care, but not the depth of social bonds. A particular bone structure can hint at agility or sensory skill, but not the cognitive processes behind them. Given these limitations, the question, who might have been first, becomes less about identifying a specific species and more about understanding the larger principle. The conditions for intelligence have existed repeatedly throughout Earth's history. Many lineages possess traits that could support its emergence. The absence of direct evidence does not prove that such intelligence never evolved. It only shows that the geological record is not equipped to capture mental complexity unless it coincides with durable technological output. This perspective also clarifies the distinction between intelligence and civilization. Intelligence is an internal trait. Civilization is an external expression with potential geological impact. A species could be highly intelligent yet leave behind no civilization at all. A species could build intricate societies based on communication, memory, or cooperation without constructing lasting structures. A species could even reach early technological stages using organic materials, wood, fibers, resins that decompose quickly. None of these pathways would leave clear evidence after millions of years. Everything we've explored so far leads to a moment where the topic becomes less about distant possibilities and more about what it means to exist right now. Earth's deep past stretches so far behind us that it makes our presence feel both improbable and temporary. When you step back and consider the scale of geological time, the notion that humans occupy only a thin slice of it becomes hard to ignore. Our species, with all its achievements and uncertainties, sits at the surface of a story that reaches far deeper than anything we normally think about in everyday life. That awareness shapes how one reflects on the idea of other potential minds or civilizations in the distant past. It also shapes how we think about our own future and our place in the long timeline of the planet. One of the strongest impressions left by the Silurian Hypothesis isn't about ancient civilizations at all. It's about limits. Not the limits of imagination, but the limits of what Earth can preserve and what humans can know. Every section of rock, every fossil, and every chemical trace represents a fraction of a world that once existed in full detail. The rest has been erased by the natural processes that keep the planet active, shifting, and alive. When you try to visualize how much has been lost, it becomes clear that the visible record is only a tiny portion of the planet's memory. This realization carries a certain humility. It reminds us that the stories we piece together from rocks and fossils represent reconstructions, not complete accounts. And yet we're here, thinking, questioning, imagining possibilities, and trying to understand where we fit. Humanity developed in the aftermath of extinctions, climate changes, and countless environmental shifts that shaped the landscape long before our species appeared. Everything we depend on today, from the ground beneath our feet to the air we breathe, is the product of billions of years of change. Our knowledge sits on a foundation built by the planet itself, and we build our interpretations from the fragments we're able to uncover and study. When someone stands in a quiet place, a forest, a desert, a coastline, and notices the texture of the ground or the shape of a rock, that material is part of a chain of events so long that it defies ordinary comprehension. Every grain of sand and every fossilized shell represents a timeline running far beyond human memory. People sometimes talk about history as though it begins with written records, but Earth's history isn't bound by those limits. It contains chapters no one will ever read because they left no surviving trace. This perspective shifts how we interpret our own moment in time. Humanity feels permanent because it's all we've ever known. Cities look solid. Languages feel fixed. Cultures seem rooted. But these impressions come from our short-lived viewpoint. Geological time reveals how quickly eras can change and how entire ecosystems can rise and fall. That awareness does not have to make our place feel insignificant. Instead, it can help clarify why it's remarkable that we're here at all. Out of all the forces that shaped the planet for billions of years, life eventually produced a species capable of reflecting on its own existence. Thinking about deep time creates a sense of connection to everything that came before. Not a connection based on specific lineage alone, but one based on continuity. The same forces that sculpted the landscapes we see today once shaped landscapes we'll never see. The same tectonic movements that carry continents across the globe now once moved regions that no longer exist. The same evolutionary processes that led to modern species once drove the rise and fall of long-lost organisms. Our presence becomes part of that larger pattern. We're another outcome of the planet's long series of experiments, another branch of the tree of life extending through time. At the same time, the idea that much of Earth's past remains unknowable encourages a certain curiosity. There's something compelling about the gaps in the record. They invite questions without demanding conclusions. They encourage imagination grounded in scientific understanding. Not imagination for the sake of inventing stories, but imagination that helps appreciate the complexity and unpredictability of evolution and geology. Recognizing how much is missing makes the surviving pieces feel more valuable. Each fossil, each sediment layer, each mineral deposit becomes a rare clue. Reflecting on our position in this immense timeline also changes how we think about future generations. If human activity continues far into the future, many of the things we build and use today will eventually disappear into the same processes that erased so much of the past. Cities will crumble, materials will degrade, landscapes will shift. Future species, or future humans, may look back on our time with the same sense of limited insight we experience when studying ancient worlds. This does not diminish the importance of what we build, it simply places our efforts in a broader context. Understanding that context can change how we see our environment. Earth is not a static place. Its ability to recycle, reshape and rework its surface is part of what makes it vibrant. Yet humans now influence those processes in ways that no other species has before. We alter landscapes quickly. We change the chemistry of the atmosphere and oceans. These changes leave signals in the geological record. Whether those signals persist for thousands or millions of years depends on how the planet responds over time. But even if they fade, they remind us that our actions contribute to a much larger story. There is something grounding about recognizing our role in this longer narrative. For all our technology, knowledge and capability, we remain part of the same natural cycles that affect every species. Our bodies rely on the same elements forged in ancient stars. Our existence depends on the same geological stability that has supported life for billions of years. Our civilizations build upon ecosystems shaped by ancient events. The fact that we can ask questions about the deep past reflects the unique position we occupy. No other species we know of has looked at the Earth and tried to reconstruct its history from scattered traces. This reflective pause leads naturally to a sense of appreciation. The ability to think about deep time, to imagine ancient possibilities, and to understand the scale of the planet's history is a human trait that comes not from technology, but from curiosity. Curiosity drives exploration, science, and the desire to know. It connects us to every generation that came before and every generation that will follow. The humbling part of this reflection comes from recognizing how temporary our place is in the geological record. No matter how enduring our structures may seem, nature will eventually reclaim them. Rivers will shift, mountains will erode, seas will rise and fall, tectonic forces will move continents. The surface of the planet will not remain as it is today. Future worlds will form where our cities once stood, just as our world formed atop ancient landscapes long forgotten. This transformation is not a threat. It's a natural part of Earth's story. Thinking about all of this in the context of the Silurian Hypothesis reveals something unexpected. The hypothesis is less about ancient civilizations and more about understanding how Earth keeps or loses records. It's a reminder that certainty is limited when dealing with deep time. It shows that humility is essential when interpreting incomplete evidence. It emphasizes that science works best when it acknowledges what it cannot know, alongside what it can. This awareness doesn't diminish the wonder of scientific discovery. Instead, it deepens it. The fact that humans can look at a thin layer of rock, a cluster of fossils, or the chemical makeup of ancient sediments and draw meaningful insights about worlds that existed hundreds of millions of years ago is extraordinary. Our ability to understand even fragments of Earth's vast story shows how far curiosity can take us. Each new discovery adds a piece to the puzzle, even as we recognize that the puzzle will never be complete. Reflecting on this brings forward another perspective. Every human life unfolds in a moment that sits between an immense past and an equally immense future. We experience only the narrowest slice of the world's timeline, yet our minds can stretch across millions of years through imagination and scientific understanding. This ability bridges the gap between the personal and the planetary. It lets us appreciate both the fragility of the present and the depth of the past. Thinking about deep time can also help guide how we approach the present. When people consider their impact on the world, it's often through immediate consequences. But geological perspective reminds us that the planet will persist long after current concerns fade. Our responsibility lies not in preserving the world unchanged, that's impossible, but in understanding how our actions interact with the processes that shape it. Being aware of deep time encourages thoughtful stewardship. It frames human influence within a context that respects both the resilience and vulnerability of the Earth. And finally, Recognizing the humbling mystery of being alive in this moment can bring a sense of connection. Across billions of years of change, life has found countless ways to survive, adapt, flourish, and sometimes fade. Humans represent one of those paths. Our appearance is part of a much longer story, and our curiosity ensures that we carry forward the desire to understand it. As we draw these reflections together, the idea isn't to reach a conclusion or offer closure. Deep time does not provide tidy endings. It offers perspective, one that continues onward into the next moment, the next discovery, and the next question that arises when we consider just how much of Earth's story remains quiet, waiting for the rare and fragile traces that happen to endure long enough for someone, somewhere, to notice and wonder what those fragments might mean.